What if the ground beneath your feet is not just dirt and rock, but a silent judge? What if every civilization that has ever risen, flourished, and then crumbled to dust did not simply fail on its own terms, but was, in a very real sense, answered by the planet itself? We do not often think of Earth as a participant in human history. We think of it as a stage, a backdrop, a resource warehouse with an infinite inventory. But what if that assumption is the most dangerous idea our species has ever embraced? What if the Earth is not passive at all, but an interconnected system of feedbacks, thresholds, and responses? And what if those responses have quietly determined which civilizations persist and which ones vanish? This is not a story about punishment. The Earth does not punish. It does not reward. It does not care. It is not sentient. It has no opinion about your cities, your governments, your monuments, or your gods, but it does respond. It responds to extraction. It responds to depletion. It responds to saturation, to overload, to disruption. And its responses are not gentle suggestions. They are physical consequences, delivered on timescales that sometimes stretch across centuries and sometimes arrive in a single catastrophic season. This documentary is an exploration of a radical but increasingly well-supported idea that the planet operates as a complex system of interlocking feedbacks, and that those feedbacks have functioned throughout the entirety of human civilization as a kind of filter. Not a conscious filter, not a moral filter, a physical one, a thermodynamic one, a biological one. Civilizations that align their structures, their consumption, their growth patterns with the regenerative capacity of the systems they depended on were granted continuity. Civilizations that did not, civilizations that overshot, that depleted, that rigidified, that ignored the signals the Earth was sending, were granted collapse. Please let us know in the comments where you are watching this documentary and what time you are watching it. And be sure to subscribe to the channel for future videos. Now let us begin at the beginning, not the beginning of human civilization, but the beginning of the system that would ultimately decide its fate. 4.5 billion years ago, a cloud of gas and dust collapsed under its own gravity. From that collapse, a star ignited. Around that star, debris coalesced into rocky bodies, and one of those bodies, the third from the sun, began a journey that would eventually produce the most complex biosphere known to exist in the universe. But Earth did not start as the lush, blue, oxygen-rich world we know. It started as a molten hellscape, bombarded by asteroids, devoid of atmosphere in any recognizable sense and utterly inhospitable to life as we understand it. What happened over the next several billion years is one of the most extraordinary stories in the history of matter itself. The planet cooled, water condensed, oceans formed, and within those oceans, chemistry became biology. Single-celled organisms emerged, organisms so simple that they would be invisible to the naked eye, yet so consequential that they would literally reshape the atmosphere of the entire planet. Cyanobacteria, among the earliest life forms, began to photosynthesize, pulling carbon dioxide from the air and releasing oxygen. This was not a minor adjustment. This was a planetary-scale transformation. Over hundreds of millions of years, these tiny organisms pumped so much oxygen into the atmosphere that they caused one of the most devastating mass extinction events in Earth's history, the Great Oxidation Event, roughly 2.5 billion years ago. The very waste product of early life, oxygen, was toxic to most of the organisms that existed at the time. Life remade the planet, and the planet, in turn, filtered which life could continue. This is the pattern. This is the template. And it has repeated in various forms ever since. The Earth is not a static object. It is a dynamic system, a web of interactions between the lithosphere, the hydrosphere, the atmosphere, and the biosphere. These four spheres do not operate independently. They are coupled. They influence each other in ways that are sometimes gradual and sometimes abrupt. The carbon cycle, for instance, is not merely a chemical process. It is a planetary thermostat, regulating temperature over geological timescales through the interplay of volcanic emissions, rock weathering, ocean absorption, and biological activity. When carbon dioxide levels rise, temperatures rise, weathering accelerates, more carbon is pulled from the atmosphere, and temperatures stabilize. When carbon dioxide levels fall, the opposite occurs. This is a feedback loop, a self-regulating mechanism that has kept Earth's temperature within a range suitable for life for billions of years, despite the fact that the sun has grown roughly 30% brighter over that same period. Think about that for a moment. The sun is significantly hotter now than it was when life first appeared. Yet the Earth has maintained conditions suitable for liquid water and biological activity for nearly 4 billion years. This is not luck. This is systemic regulation. The planet's interlocking feedback mechanisms have, over deep time, maintained a kind of dynamic equilibrium, not a fixed state, but a bounded range of conditions within which life can persist and evolve. This concept, sometimes associated with the Gaia hypothesis proposed by James Lovelock and Lynn Margulies in the 1970s, does not require any mystical interpretation. It does not require consciousness. It does not require intention. It simply requires the recognition that when you have a system with multiple interacting components that influence each other's behavior, that system will exhibit emergent properties, behaviors that arise from the interactions themselves rather than from any single component. Earth's climate stability is an emergent property. The oxygen content of the atmosphere is an emergent property. The salinity of the oceans is an emergent property. None of these are managed by any central authority. They are maintained by the constant interplay of physical, chemical, and biological processes. And here is the critical insight for our purposes. Those emergent properties create the conditions within which civilizations either thrive or fail. The climate determines where crops can grow. The water cycle determines where rivers flow and aquifers fill. The nutrient cycles in the soil determine how much food a given area of land can produce. The stability of coastlines determines where ports can be built. The predictability of seasons determines when to plant and when to harvest. Every single foundation of human civilization rests upon the stability of Earth's interlocking systems. And those systems are not infinitely tolerant. They have thresholds, they have tipping points. They have limits beyond which they shift into new states, states that may be perfectly stable from a planetary perspective but utterly catastrophic from a human one. The Earth does not care which state it is in. A planet covered in ice is just as physically valid as a planet with tropical forests at the poles. A planet with atmospheric carbon dioxide levels 10 times higher than today's is just as physically valid as one with levels 10 times lower. The planet has been in all of these states at various points in its history, and it will be in others in the future. The question is not what state the Earth prefers. The Earth has no preferences. The question is what state allows human civilization to continue, and whether human civilization is pushing the planet toward a state that does not. To understand how Earth systems interact with human societies, we need to understand something about the nature of feedback itself. Feedback is one of the most important concepts in systems theory, and it comes in two fundamental forms: negative feedback and positive feedback. Negative feedback is stabilizing. It pushes a system back toward equilibrium when it deviates. A simple example: when your body temperature rises, you sweat. Sweating cools you down. Your temperature returns to normal. The deviation triggered a response that counteracted the deviation. This is negative feedback. Earth's climate system is full of negative feedbacks. When temperatures rise, evaporation increases, which increases cloud cover, which reflects more sunlight back into space, which cools the surface. When temperatures fall, ice sheets expand, but eventually the reduction in weathering allows carbon dioxide to build up in the atmosphere, which warms the planet again. These are slow, grinding processes, operating over thousands or millions of years, but they are remarkably effective at maintaining conditions within a livable range. Positive feedback, on the other hand, is destabilizing. It amplifies deviations rather than counteracting them. When Arctic ice melts, it exposes dark ocean water, which absorbs more heat than ice would, which causes more ice to melt, which exposes more dark water. The initial change accelerates itself. Positive feedback loops are what drive systems past tipping points, past the thresholds beyond which negative feedbacks can no longer restore the previous equilibrium. The system shifts to a new state. Human civilizations, like all complex systems, are also governed by feedback. And the feedback that matters most, the feedback that determines whether a civilization persists or collapses, is the feedback between the civilization and the planetary systems it depends on. When a society cuts down forests to create farmland, it receives positive feedback in the form of increased food production. But it also triggers a cascade of secondary effects: soil erosion, altered water cycles, reduced biodiversity, changes in local climate. If the society pays attention to these secondary effects and adjusts its behavior, reducing deforestation, implementing soil conservation, allowing forests to regenerate, it maintains the negative feedback loop that keeps the system in balance. If it ignores the secondary effects and continues to cut, the positive feedback loop of degradation accelerates. Soil becomes thinner, yields decline, more forest must be cut to compensate, the degradation deepens. Eventually, the land can no longer support the population and the civilization faces crisis. This is not a hypothetical scenario. This is the actual mechanism by which dozens of documented civilizations have declined or collapsed throughout human history. The details vary, the crops are different, the landscapes are different, the political structures are different. But the underlying dynamic is the same. A society extracts from its environment faster than the environment can regenerate, ignores or fails to perceive the feedback signals indicating degradation, and eventually crosses a threshold beyond which recovery is either impossible or insufficient to sustain the existing level of complexity. The word ignores in the previous paragraph is doing a great deal of work, and it deserves closer examination. Why do societies ignore environmental feedback? This is one of the most important questions in the study of civilizational collapse, and the answers are varied but instructive. Sometimes the feedback is genuinely difficult to perceive. Environmental degradation often occurs slowly, over generations. Each generation inherits a slightly diminished environment but has no memory of the original state. This phenomenon, sometimes called shifting baseline syndrome, means that what appears normal to the current generation would have appeared devastated to their great-grandparents. A fisherman who catches half as many fish as his father did may consider this normal if he never experienced his father's catches. His son, catching half as many as he does, will consider that normal in turn. The baseline shifts downward with each generation, and the cumulative degradation becomes invisible. Sometimes the feedback is perceived but misinterpreted. A society that experiences declining crop yields may attribute the decline to insufficient prayers to the gods, to the moral failings of the population, to the machinations of enemy nations, to anything other than the actual cause, soil depletion. If the diagnosis is wrong, the response will be wrong, and the degradation will continue. Sometimes the feedback is perceived and correctly interpreted, but the society lacks the political or economic structures to respond effectively. The individuals who benefit most from the current pattern of extraction are often the most powerful members of society, and they have strong incentives to resist change. A ruling class that derives its wealth and power from intensive agriculture on degrading land may understand perfectly well that the land is degrading, but may calculate correctly or incorrectly that the costs of changing course outweigh the costs of continuing, at least for them, at least for now. The costs of degradation are often distributed broadly across the population, while the benefits of extraction are concentrated among the elite. This asymmetry of costs and benefits is one of the most common drivers of civilizational overshoot, and sometimes the feedback is perceived, correctly interpreted, and the society has the capacity to respond, but it responds too late. There is a lag between action and consequence in complex systems. The carbon dioxide emitted today will warm the planet for decades or centuries to come. The topsoil eroded today will take thousands of years to regenerate. The aquifer depleted today will take tens of thousands of years to refill, if it refills at all. By the time the consequences of past actions become severe enough to demand a response, the window for effective response may have already closed. All of these dynamics, perception failure, misinterpretation, structural incapacity, and temporal lag, are features of the interface between human civilizations and planetary systems. They are the mechanisms by which the planet's physical filter operates on human societies. The filter does not require intention. It does not require judgment. It simply requires that the planet's systems continue to operate according to the laws of physics and chemistry, and that those laws impose real, non-negotiable constraints on what human societies can extract, emit, and disrupt without consequence. Let us now turn to the historical record and examine how this filter has operated in practice. We will begin not with the most famous examples of civilizational collapse, but with one of the earliest and most instructive, the societies of ancient Mesopotamia. Mesopotamia, the land between the Tigris and Euphrates rivers in what is now modern-day Iraq, is often called the cradle of civilization. It was here, roughly 10,000 years ago, that some of the first agricultural societies emerged. The alluvial plains of Mesopotamia were extraordinarily fertile, deposited by millennia of river flooding that spread nutrient-rich silt across the landscape. Early farming communities discovered that they could grow crops in this rich soil with remarkable productivity, and that they could further increase yields by diverting river water through irrigation channels to water fields that would otherwise be too dry to farm. Irrigation was one of the great technological achievements of early civilization. It allowed societies to expand agricultural production far beyond what rain-fed farming could support, enabling larger populations, greater social complexity, surplus accumulation, trade, writing, cities, and all the other hallmarks of what we call civilization. The great city-states of Sumer, Akkad, Babylon, and Assyria were all built, in a very literal sense, on irrigated agriculture. But irrigation in an arid environment carries a hidden cost, a cost that operates on timescales longer than a human lifetime and is therefore easy to miss. When water is applied to fields in a dry climate, it evaporates rapidly from the soil's surface. As it evaporates, it leaves behind the dissolved salts that were present in the water. Over years and decades, these salts accumulate in the topsoil. The process is called salinization, and its effects on agriculture are devastating. As salt concentrations increase, crop yields decline. Plants struggle to absorb water from soil that is saturated with salt. Eventually, if the process continues long enough, the land becomes too saline to grow anything at all. The Sumerians knew this was happening. Archaeological evidence, including ancient agricultural records written in cuneiform on clay tablets, documents a shift in crop choice over time. Early records show a mix of wheat and barley cultivation. Later records show an increasing emphasis on barley, which is more salt-tolerant than wheat. Still later records show declining yields even of barley. The society was adapting, but it was adapting within a framework that could not address the root cause. The irrigation continued because the population depended on it. The salinization continued because the irrigation continued. The society was trapped in a feedback loop that it could not escape without fundamentally restructuring its agricultural system, and that restructuring was politically, economically, and socially impossible within the existing power structures. The consequences unfolded over centuries, not overnight. The great city-states of southern Mesopotamia gradually declined. Power shifted northward to regions where salinization had not yet progressed as far. But the same pattern repeated in the new centers of power because the same agricultural techniques were employed. The land between the rivers, once the most productive agricultural region in the world, was gradually degraded by the very practices that had made it productive. Today, much of southern Iraq remains affected by salinization, a legacy of decisions made thousands of years ago. This is the planetary filter in action. The earth did not punish the Sumerians. It did not judge their social structure or their religious beliefs or their artistic achievements. It simply responded to the physical consequences of their agricultural practices. Water was applied to soil. Evaporation occurred, salts accumulated, yields declined. The planet's response was entirely mechanical, entirely predictable, and entirely indifferent to the human drama that unfolded as a result. Consider now a very different environment, a very different civilization, and a very different mechanism of the same fundamental process. The classic Maya civilization, which flourished in the lowland tropical forests of Central America from roughly the 3rd to the 9th centuries of the Common Era, represents one of the most extensively studied examples of civilizational decline in the archaeological record. The Maya built one of the most sophisticated civilizations of the ancient world. Their cities were architectural marvels, their mathematical and astronomical knowledge was extraordinary, their writing system was the most complete in the pre-Columbian Americas, and their agricultural techniques were ingeniously adapted to the challenging environment of the tropical lowlands. They practiced slash-and-burn agriculture, terracing, raised field farming in wetland areas, and agroforestry. They managed water through elaborate systems of reservoirs, canals, and catchment basins. For centuries, their system worked, but the Maya lowlands are an environment with thin, fragile soils that depend on forest cover for their fertility. The nutrients in a tropical forest are not primarily stored in the soil, as they are in temperate regions. They are stored in the biomass itself, in the trees and plants and the organic matter on the forest floor. When forest is cleared for agriculture, the nutrients are briefly available in the exposed soil, but they are rapidly depleted by the heavy tropical rains that leach them away. Sustained agriculture in such an environment requires either long fallow periods to allow forest regrowth and nutrient recovery, or intensive management practices that artificially maintain soil fertility. During the late Classic period, roughly the 7th through 9th centuries, Maya population density reached levels that may have been unsustainable for the agricultural systems in place. More land was cleared, fallow periods were shortened, marginal lands, hillsides, and areas with particularly thin soils were brought into cultivation. Deforestation accelerated, and with it, a cascade of environmental consequences. Erosion intensified. The clay soils beneath the thin organic layer were exposed, soils that were far less productive and far more prone to waterlogging and compaction. Sediment from eroded hillsides filled reservoirs and wetland areas, reducing their capacity to store water. And then the rains changed. Paleoclimate records derived from lake sediment cores, cave stalagmites, and ocean sediment samples reveal that the 9th century in the Maya lowlands was punctuated by a series of prolonged droughts. These were not unprecedented in the region's climate history. The Maya lowlands had experienced droughts before, but the droughts of the 9th century struck a landscape and a society that were already stressed. The forests that had once moderated local climate and maintained moisture in the atmosphere had been significantly reduced. The reservoirs that had stored water during dry periods had been partially filled with eroded sediment. The soils that had once been buffered by deep organic layers had been thinned and degraded. The droughts of the 9th century were not the sole cause of the classic Maya collapse. The causes were multiple and interacting: political fragmentation, warfare between city-states, disruption of trade networks, social unrest. But the environmental dimension, the degradation of the agricultural base combined with climatic stress, created the conditions within which all of these other factors became lethal. A society with healthy soils, intact forests, and full reservoirs might have weathered the droughts with difficulty, but without disintegration. A society with depleted soils, reduced forests, and compromised water storage could not. The pattern is the same as in Mesopotamia, expressed through different mechanisms. The society extracted from its environment at a rate that exceeded regeneration. The environment degraded. Climatic perturbation that might have been manageable in a healthy system became catastrophic in a degraded one. The society contracted, fragmented, and in many areas collapsed entirely. Cities that had housed tens of thousands of people were abandoned to the forest. Within a few generations, the jungle reclaimed what had taken centuries to build. Again, the earth did not target the Maya. It did not select them for destruction. It simply continued to operate according to its physical laws. Rain fell on exposed soil and carried it away. Trees that were cut did not moderate the local climate. Reservoirs that were silted could not store water. Each of these was a physical consequence of a physical action, linked together in a web of cause and effect that the Maya could not fully perceive and could not adequately address within their existing social and political frameworks. The examples could be multiplied extensively. The ancestral Puebloan societies of the arid Southwest experienced a remarkably similar pattern of environmental stress, resource depletion, and climatic perturbation, leading to dramatic social reorganization and abandonment of previously thriving settlements. The Great Center at Chaco Canyon, with its massive multi-story great houses and elaborate road network, was sustained by an agricultural system that was always marginal in the arid environment and became untenable when a prolonged drought struck in the 12th century. The Chacons had already deforested the surrounding landscape to obtain construction timber, altering local water flow patterns and reducing the land's capacity to retain moisture. When the rains failed, the system failed with them. The Khmer Empire, centered on the great city of Angkor in what is now Cambodia, built one of the most elaborate water management systems in the pre-industrial world. A vast network of reservoirs, called barrays, canals, and channels captured, stored, and distributed monsoon rains to support intensive rice agriculture across a landscape that experienced dramatic seasonal variation in rainfall. Angkor, at its peak in the 12th and 13th centuries, may have been the largest city in the world, covering an area of roughly 1,000 square kilometers and supporting a population of several 100,000 or more. The entire system depended on the precise management of water. Over time, the water management infrastructure aged and degraded. Sedimentation from deforestation and agriculture filled channels and reservoirs. Erosion damaged the carefully engineered earthworks that controlled water flow. And when the climate shifted, as paleoclimate records indicate it did during the 14th and 15th centuries, with increasingly erratic monsoon patterns and periods of both drought and extreme flooding, the degraded infrastructure could not adapt. The system that had sustained one of the ancient world's greatest cities became its vulnerability. Angkor declined, its population dispersed, and the forest gradually consumed the temples and reservoirs that had once represented the pinnacle of hydraulic engineering. In each of these cases, the narrative is not one of sudden catastrophe, but of gradual degradation. The collapse was not an event, it was a process, and the process was driven by the interaction between human extraction and planetary response. The civilizations did not fail because they were unintelligent. They failed because the systems they built were optimized for current conditions and could not adapt when those conditions changed, especially when the change was driven, at least in part, by their own actions. This brings us to one of the most important concepts in understanding how planetary systems filter civilizations, the concept of complexity and its relationship to resilience. Joseph Tainter, in his influential work on the collapse of complex societies, argued that civilizations tend to respond to problems by increasing their complexity. When a society faces a challenge, whether it is a food shortage, a military threat, an administrative problem, or an environmental stressor, it typically responds by adding new layers of organization, new specialists, new institutions, new infrastructure. Each addition solves the immediate problem but also increases the overall complexity of the system. And complexity has costs. Each new layer of organization requires energy and resources to maintain. Each new specialist must be fed, housed, and compensated. Each new institution requires administration. Each new piece of infrastructure requires maintenance. In the early stages of a civilization's development, the returns on complexity are high. The first irrigation channels dramatically increase food production relative to their cost. The first administrative systems significantly improve coordination relative to their overhead. The first military organizations effectively protect against threats relative to their expense. But over time, the returns on additional complexity diminish. The 100th irrigation channel provides less marginal benefit than the first. The 10th layer of bureaucracy provides less marginal improvement in coordination than the first. The society must invest more and more resources to achieve smaller and smaller gains. This dynamic, which Tainter calls the declining marginal returns on complexity, creates a trap. The society becomes dependent on its complex systems. It cannot simplify without losing functionality, but it cannot maintain its complexity without ever increasing resource inputs. As long as resources are abundant, this is manageable. But when resources become constrained, whether due to environmental degradation, climate change, or simple depletion, the society faces a crisis. It cannot afford its own complexity, but it cannot function without it. This is where the planetary filter operates with particular ruthlessness. A complex society that has depleted its resource base is in a fundamentally different position than a simple society facing the same environmental challenge. The simple society has fewer dependencies, fewer vulnerabilities, fewer points of potential failure. It can adapt more easily because it has less to adapt. The complex society, with its elaborate infrastructure, its specialized workforce, its intricate supply chains, its centralized administration, has more to lose and less flexibility with which to respond. When the environment shifts, the complex society's very sophistication becomes its greatest liability. Consider two hypothetical farming communities facing a drought. The first is a small village where each family grows its own food, stores its own water, and maintains its own tools. When the drought comes, each family must cope independently. Some will succeed and some will fail, but the failures do not cascade. The loss of one family does not threaten the survival of the others. The second is a large, complex agricultural system where food is grown on specialized farms, processed in centralized facilities, transported through an elaborate distribution network, and purchased by urban consumers who grow none of their own food. When the drought comes, the farms produce less. The processing facilities receive less input. The distribution network has less to distribute. The urban consumers who have no capacity to grow their own food face shortages. The entire system is stressed simultaneously because every part depends on every other part. A disruption at the base, in this case agricultural production, cascades upward through every level of the system. This is not merely a theoretical exercise. This is the structure of every advanced civilization that has ever existed, including our own. And it is the structure that makes advanced civilizations most vulnerable to the planetary filter. The same complexity that enables extraordinary achievements in art, science, governance, and technology also creates extraordinary vulnerability to disruptions in the resource base that supports it all. The Earth does not distinguish between simple and complex societies in its physical responses. Rainfall does not discriminate, soil erosion does not discriminate, aquifer depletion does not discriminate, but the consequences of these physical processes are profoundly different for societies of different levels of complexity. A simple society can bend. A complex society, if it cannot adapt its structures quickly enough, can shatter. Let us pause here and consider a deeper question, one that goes beyond the mechanics of feedback and collapse. Why does the pattern repeat? If civilizations throughout history have been filtered by the same basic dynamic, extraction exceeding regeneration followed by degradation followed by crisis, why has each successive civilization not learned from its predecessors and avoided the same fate? Part of the answer is the one we have already discussed, the difficulty of perceiving slow, cumulative environmental change. But there is a deeper answer, one that relates to the fundamental structure of human societies and the incentive systems that govern human behavior. Human societies are not unitary actors. They are composed of individuals and groups with differing interests, differing time horizons, and differing levels of power. The decisions that drive civilizational trajectory are not made by the civilization as a whole, but by individuals and groups who are responding to their own immediate incentives. A farmer who clears forest to plant crops is not thinking about the long-term consequences for regional hydrology. He is thinking about feeding his family this year. A ruler who orders the construction of a massive monument is not thinking about the resource depletion that will result. She is thinking about consolidating her political power in the present. A merchant who trades in a scarce resource is not thinking about the long-term sustainability of the supply. He is thinking about the profit to be made today. None of these individuals are irrational. Each is making a perfectly reasonable decision within the context of their own situation, knowledge, and incentives. The problem is that the sum of individually rational decisions can be collectively catastrophic. This is the tragedy of the commons, articulated by Garrett Hardin in 1968, but understood in various forms for centuries. When a shared resource is available to all, and when each individual benefits from exploiting it but the costs of exploitation are shared by everyone, the resource will tend to be overexploited. Each individual gains the full benefit of their own use but bears only a fraction of the cost. The incentive structure drives the system toward depletion. This dynamic is not a failure of intelligence or morality. It is a structural feature of how human societies interact with shared resources. Overcoming it requires institutional mechanisms that align individual incentives with collective long-term interests, mechanisms like regulations, property rights, community management systems, cultural norms, and governance structures that enforce sustainable use. Such mechanisms have existed in many societies throughout history, and some have been remarkably effective for extended periods. But they are always under pressure from the short-term incentives that push toward exploitation, and they tend to weaken as societies grow larger, more complex, and more stratified. In a small community where everyone knows each other and the consequences of overuse are immediately visible, social pressure can be an effective mechanism for managing shared resources. In a large, anonymous society where the consequences of overuse are distant in space and time, social pressure is far less effective. The farmer who depletes the soil on his own land suffers the consequences directly. The corporation that depletes an aquifer that supplies water to millions may never experience any direct consequence at all, because the consequences fall on others and they fall slowly over decades. This is the human dimension of the planetary filter. The Earth's physical systems do not care about the social dynamics that drive overexploitation. They respond only to the physical reality. Soil is either depleted or it is not. Water tables are either falling or they are not. Carbon dioxide concentrations are either rising or they are not. The social dynamics determine whether the society will act to address these physical realities, but the physical realities proceed regardless of whether the society acts or not. We have spoken extensively about terrestrial examples, about soil, water, forests, and agriculture. But the planetary filter operates through many other channels as well, and one of the most important is climate itself. Climate is not merely the backdrop against which civilizations operate, it is an active participant in their fate. Human civilizations emerged during the Holocene epoch, the roughly 11,700-year period following the last ice age. The Holocene has been characterized by remarkable climatic stability, at least by the standards of Earth's geological history. Temperatures have varied, precipitation patterns have shifted, and there have been periods of significant climatic stress. But compared to the wild swings of the Pleistocene, the epoch that preceded it, the Holocene has been a period of unusual calm. This calm was not guaranteed. It was a feature of the particular configuration of Earth's orbital parameters, atmospheric composition, ocean circulation patterns, and ice sheet extent that prevailed during this period. And it was this calm that made agriculture possible. Agriculture requires predictability. It requires that the farmer can reasonably expect that the rains will come at roughly the same time each year, that the growing season will be roughly the same length, that the temperatures will fall within a range that the crops can tolerate. The wild climatic oscillations of the Pleistocene, with temperatures swinging by several degrees Celsius over decades, would have made sustained agriculture nearly impossible. The stability of the Holocene provided the platform on which the entire edifice of human civilization was built. But within the Holocene's overall stability, there have been significant climatic fluctuations, and those fluctuations have had profound effects on human societies. The period from roughly 900 to 1300 of the Common Era, sometimes called the medieval warm period, was characterized by warmer than average temperatures in many parts of the world. This warmth expanded the range of viable agriculture in some regions. Vineyards flourished in parts of northern Europe where they could not grow before. Norse settlers established agricultural colonies in Greenland and Iceland. Populations grew, civilizations expanded, then the climate shifted. The period from roughly the 14th through the 19th centuries, sometimes called the Little Ice Age, brought cooler temperatures, more variable weather, and in some regions, significantly reduced growing seasons. Norse colonies in Greenland, which had been marginal even during the warm period, became untenable. The settlers, who had maintained a European pastoral farming style dependent on cattle grazing, found that their pastures could no longer support their herds. The sea ice expanded, cutting off the shipping routes that connected them to Europe. The colony declined and eventually vanished entirely. The Greenland Norse are a particularly instructive case because their fate was not simply determined by climate. The Inuit, who inhabited the same island during the same period, not only survived the cooling but thrived. The difference was not genetic or intellectual. It was cultural and technological. The Inuit had developed a suite of technologies and practices: kayaks, toggling harpoons, ice fishing, seal hunting on sea ice, cold weather clothing made from animal skins that were precisely adapted to the Arctic environment. The Norse, by contrast, maintained the agricultural and pastoral practices of their European homeland, practices that were poorly suited to the harsh conditions and became entirely unsuitable when the climate cooled. They had the opportunity to adopt Inuit practices. Archaeological and historical evidence suggests that they were aware of these practices, but for cultural, religious, or social reasons, they chose not to. Here we see the planetary filter operating in its most nuanced form. The climate shift did not destroy all human habitation on Greenland. It destroyed a particular form of human habitation, one that was rigidly committed to a set of practices that were incompatible with the new conditions. The Inuit, whose practices were compatible, continued. The earth did not select for a particular people. It selected for a particular relationship with the environment. The Norse relationship, based on imported practices that worked well in a different climate, was filtered out. The Inuit relationship, based on practices developed in and for the Arctic, was permitted to continue. This distinction is crucial. The planetary filter does not operate on people. It operates on systems. It operates on the structures, practices, technologies, and institutions through which people interact with their environment. A society that maintains flexible, adaptive systems can survive environmental shifts that would destroy a society with rigid, inflexible ones. The filter selects for adaptability, not for any particular culture, ethnicity, or level of technological development. Let us now consider what the deep geological record can tell us about the planetary filter, because the record of mass extinctions, the most dramatic instances of the filter operating on life as a whole, offers profound lessons for understanding its operation on human civilizations. Earth has experienced 5 major mass extinction events in the last 540 million years, events in which a significant fraction of all species on the planet went extinct in a geologically brief period. These events were driven by different causes: asteroid impacts, massive volcanic eruptions, rapid climate change, ocean chemistry shifts, and combinations of these and other factors. But they all share certain features that are relevant to our discussion. First, in every mass extinction, the species that went extinct were not the weakest or the least successful. Many of them were among the most dominant organisms of their time. The trilobites that vanished in the Permian extinction had been successful for over 250 million years. The non-avian dinosaurs that disappeared at the end of the Cretaceous had dominated terrestrial ecosystems for over 150 million years. Dominance in one environmental regime does not guarantee survival when that regime changes. In fact, dominance can be a liability because dominant organisms tend to be highly specialized for the conditions in which they became dominant. When those conditions change, their specialization becomes a trap. Second, the survivors of mass extinctions were not necessarily the largest, the strongest, or the most complex. They were the most adaptable. They were the organisms that could tolerate a wider range of conditions, that could exploit a broader range of food sources, that could survive in a greater diversity of habitats. They were, in a word, generalists. The small, burrowing mammals that survived the end Cretaceous extinction were not superior to the dinosaurs in any obvious way. They were not bigger, not faster, not more powerful, but they were more flexible. They could eat a wider range of foods. They could tolerate a wider range of temperatures. They could survive in a wider range of environments. When the asteroid struck and the world changed, the mammal's flexibility was the trait that mattered, not the dinosaur's size or strength. Third, mass extinctions are followed by periods of rapid evolutionary radiation, periods in which the survivors diversify rapidly to fill the ecological niches vacated by the extinct species. The extinction itself is a catastrophe, but the aftermath is a period of extraordinary creativity and innovation, as life explores new possibilities in a transformed landscape. The mammals that survived the end Cretaceous extinction diversified within a few million years into an astonishing array of forms: whales, bats, elephants, primates, rodents, and eventually us. The extinction cleared the way for new forms of life that could not have emerged while the old forms dominated. These patterns, the vulnerability of the dominant and specialized, the survival of the flexible and adaptable, and the creative explosion that follows catastrophe, are not merely biological phenomena. They are features of complex adaptive systems in general, and they apply to human civilizations as well. The most powerful and complex civilizations are often the most specialized, the most dependent on specific conditions, and the most vulnerable to changes in those conditions. The smaller, more flexible, more diversified societies are often better positioned to survive environmental shifts. And the collapse of a dominant civilization, while catastrophic for those who lived within it, often creates the conditions for new social forms to emerge, forms that are better adapted to the new environmental reality. This is not to romanticize collapse. Collapse is a human catastrophe. People suffer, people die, knowledge is lost, art is destroyed. The accumulated achievements of generations are erased. There is nothing desirable about civilizational collapse, and the purpose of understanding its mechanisms is not to accept it as inevitable, but to learn how to prevent it. But preventing it requires understanding the dynamics that drive it, and those dynamics are, at their root, the dynamics of complex systems interacting with the physical constraints of the planet. Let us go deeper into the mechanics of how ecosystems maintain themselves, because this understanding is essential to grasping why human disruption of these systems carries such severe consequences. An ecosystem is not merely a collection of organisms occupying the same space. It is a web of relationships, energy flows, nutrient cycles, and feedback mechanisms that together create a self-sustaining system. Each species in an ecosystem plays a role, often multiple roles, in maintaining the system's overall function. Predators regulate herbivore populations. Herbivores regulate plant growth. Plants stabilize soil, regulate water flow, and convert solar energy into forms that other organisms can use. Decomposers break down dead organic matter and return nutrients to the soil, where they become available to plants again. Fungi form vast underground networks that connect trees and facilitate the exchange of nutrients and chemical signals. Insects pollinate plants, aerate soil, and serve as food for birds and other animals. Every component is connected to every other component through multiple pathways. This interconnection gives ecosystems their resilience. If one pathway is disrupted, others can compensate. If one species declines, others can partially fill its role. The system has redundancy built into it, not by design but by the process of evolution operating over millions of years. Each connection was forged by natural selection, tested by environmental change, and refined by competition and cooperation. The result is a system of extraordinary robustness, capable of absorbing significant shocks and returning to a functional state, but this robustness has limits. When too many connections are severed, when too many species are removed, when too many pathways are disrupted, the system's capacity to compensate is overwhelmed. The system enters a state of degradation from which recovery is slow, difficult, and sometimes impossible within human timescales. And the critical insight is that the system does not degrade linearly. It does not lose function in proportion to the amount of disruption. It absorbs disruption, absorbs it, apparently unaffected, and then suddenly and catastrophically it shifts to a degraded state. This is the tipping point phenomenon, and it is one of the most dangerous features of the planetary filter. Consider a lake that receives nutrient runoff from surrounding farmland. As nitrogen and phosphorus from fertilizers flow into the lake, algae populations increase. For a time, the lake's ecosystem absorbs this additional nutrient load. Aquatic plants, fish, and other organisms adjust. The water remains clear. An observer might conclude that the nutrient runoff is having no significant effect, but beneath the surface, the system is being stressed. Nutrient concentrations are rising, algae populations are growing, oxygen levels are beginning to fluctuate. Then one summer, the threshold is crossed. The algae bloom explosively, covering the surface of the lake in a thick green mat. The bloom blocks sunlight from reaching underwater plants, which die. Their decomposition consumes oxygen, creating dead zones where fish and other aerobic organisms suffocate. The clear, productive lake has transformed into a murky, oxygen-depleted, biologically impoverished body of water, and the transformation is very difficult to reverse. Even if nutrient inputs are immediately stopped, the lake may remain in its degraded state for years or decades. because the feedback mechanisms that maintain the clear water state have been disrupted, and new feedback mechanisms that maintain the degraded state have taken their place. This dynamic, the sudden shift from one stable state to another after a gradual buildup of stress, is characteristic of complex systems in general and of Earth systems in particular. Coral reefs shift from coral-dominated to algae-dominated states. Grasslands shift to desert, forests shift to scrubland. Ice sheets, once they begin to retreat, can enter self-reinforcing cycles of decline. Ocean circulation patterns can reorganize abruptly. The climate itself can shift between states, and in every case, the shift is preceded by a period of apparent stability during which the stress is accumulating invisibly. This is why the planetary filter is so effective and so dangerous. It does not announce itself. It does not provide clear, unambiguous warnings. It allows civilizations to continue their patterns of extraction and disruption for years, decades, even centuries, absorbing the consequences in ways that are not immediately apparent. And then when the threshold is crossed, the consequences arrive not gradually but suddenly, not proportionally but catastrophically. The concept of thresholds and tipping points is central to understanding the relationship between human civilizations and planetary systems, and it bears further exploration. In recent decades, Earth system scientists have identified a number of critical thresholds in the planet's systems, thresholds that, if crossed, could trigger cascading changes with consequences far beyond the initial disruption. These thresholds exist in the climate system, the biosphere, the ocean chemistry, the freshwater cycle, and the nutrient cycles. They are interconnected. Crossing one threshold can push others closer to their own tipping points, creating the possibility of a cascade of transitions that could fundamentally alter the state of the planet on timescales far shorter than those of geological change. The ice sheets of the polar regions, for example, play a critical role in regulating global temperature. Their white surfaces reflect solar radiation back into space, cooling the planet. As temperatures rise and ice melts, the reflective surface shrinks, more solar radiation is absorbed by the dark ocean and land beneath, and temperatures rise further. This positive feedback loop can drive the system toward a state of significantly reduced ice coverage, which in turn raises sea levels, alters ocean circulation patterns, and changes weather patterns across the globe. Once set in motion, this process is very difficult to stop because the feedback mechanism that drives it is self-reinforcing. The world's tropical forests, particularly the great forests of the Amazon basin, the Congo basin, and Southeast Asia, play a similarly critical role. These forests do not merely respond to climate, they create it. Through transpiration, the process by which trees release water vapor through their leaves, tropical forests generate a significant fraction of their own rainfall. The moisture that evaporates from the forest canopy rises, condenses, and falls as rain, which the forest absorbs and transpires again, cycling the same water multiple times across the landscape. This recycling of moisture allows the interior of large tropical forests to receive far more rainfall than the distance from the coast would otherwise permit. When forest is cleared, this moisture recycling is disrupted. Less water is transpired, less rain falls. The remaining forest dries out and becomes more susceptible to fire. Fires destroy more forest, further reducing transpiration and rainfall. Enough forest is cleared, the system can cross a tipping point beyond which the remaining forest can no longer maintain sufficient moisture to sustain itself. The forest shifts to a savanna or grassland state, a state that is stable but profoundly different from the forest it replaced. The loss is not merely ecological. It is hydrological, climatic, and ultimately civilizational, because billions of people depend on the rainfall patterns that these forests maintain. The ocean, too, has thresholds. The absorption of carbon dioxide by seawater produces carbonic acid, which lowers the pH of the ocean. This process, called ocean acidification, threatens the ability of calcifying organisms, corals, shellfish, and certain species of plankton, to build and maintain their shells and skeletons. These organisms are not minor components of the marine ecosystem. Coral reefs support roughly a quarter of all marine species. Calcifying plankton form the base of many marine food chains. Their decline or loss would ripple through the entire ocean ecosystem with consequences that are difficult to predict in detail, but almost certainly severe. Each of these thresholds exists within a web of connections to the others. Climate warming drives ice melt, which drives further warming. Forest loss reduces carbon absorption, which drives further warming. Ocean acidification reduces the ocean's capacity to absorb carbon, which drives further warming. Warming drives more extreme weather, which stresses forests and agricultural systems, which reduces food security, which stresses human societies, which reduces their capacity to address the underlying drivers. The system is not a collection of independent problems. It is a single, interconnected problem, and its components can reinforce each other in ways that accelerate the overall trajectory. Now let us consider a concept that is often overlooked in discussions of civilizational sustainability, but is absolutely fundamental to understanding the planetary filter: the concept of energy, and specifically the concept of energy return on investment. Every civilization requires energy. Energy to grow food, energy to build structures, energy to transport goods, energy to heat homes, energy to power industry, energy to maintain the infrastructure of daily life. The form of this energy has changed over time, from human and animal muscle to wood to coal to oil to natural gas to nuclear fission to, increasingly, renewable sources like solar and wind. But the fundamental requirement has not changed. Civilization requires energy, and the amount of energy required increases with the level of complexity. Energy return on investment, sometimes abbreviated as EROI, is a measure of how much energy a society gets back for each unit of energy it invests in obtaining energy. If a society invests 1 unit of energy and gets back 30 units, its EROI is 30 to 1. If it invests 1 unit and gets back 5 units, its EROI is 5 to 1. If it invests 1 unit and gets back 1 unit, its EROI is 1 to 1, and there is no net energy gain. The civilization cannot sustain itself on an energy source with an EROI of 1 to 1, because there is no surplus energy left over to do anything other than obtain more energy. The history of human civilization can be read in part as a history of energy transitions driven by changes in EROI. Pre-agricultural societies derived their energy from foraging and hunting, activities with moderate EROI but limited total energy yield. The transition to agriculture dramatically increased the total energy available to society, because domesticated plants convert solar energy into food far more efficiently, from a human perspective, than wild plants do. The EROI of early agriculture was very high, perhaps 50 to 1 or more, depending on the crop and the environment. This surplus energy, the energy left over after the costs of farming were met, was what made possible all the other activities of civilized life: construction, trade, art, governance, warfare, science. As civilizations grew and their environments were degraded, the EROI of agriculture declined. More energy had to be invested to maintain yields, more labor to clear new land, more effort to irrigate, more work to manage soil fertility. The surplus shrank. And when the surplus shrank below the level needed to maintain the civilization's complexity, the civilization was in trouble. The transition to fossil fuels, beginning with coal in the 18th century and accelerating with oil and natural gas in the 19th and 20th centuries, represented an extraordinary increase in available energy. Fossil fuels are concentrated stores of ancient solar energy, captured by photosynthetic organisms over hundreds of millions of years and compressed into energy-dense forms by geological processes. The EROI of early oil production was astonishingly high, perhaps 100 to 1. A small amount of energy invested in drilling a well and pumping oil out of the ground yielded an enormous return. This surplus energy powered the Industrial Revolution, the explosive growth of population, the globalization of trade, the mechanization of agriculture, the construction of modern cities, and every other feature of the modern world. But the EROI of fossil fuels has been declining. The easy-to-access deposits have been exploited first, as they always are. What remains is deeper, more remote, more technically challenging, and more energy-intensive to extract. The EROI of oil production has declined from roughly 100 to 1 in the early 20th century to roughly 15 to 1 or less in many producing regions today. For some sources, such as oil sands and deep water drilling, the EROI is much lower, perhaps 5 to 1 or even 3 to 1. As EROI declines, a larger fraction of the energy produced must be reinvested in energy production itself, leaving less surplus energy available for everything else. This is not merely an economic or technical challenge, it is a civilizational one. A society accustomed to an EROI of 100 to 1 operates very differently from a society with an EROI of 10 to 1. The first society has enormous surplus energy with which to maintain its complexity, fund innovation, support non-productive activities like art and research, and absorb shocks. The second society has much less margin. It must make harder choices about how to allocate its more limited energy surplus. It is less able to invest in the future because it is more fully occupied with meeting the demands of the present. The planetary filter operates here with inexorable logic. Energy sources are physical. Their availability is governed by geology, physics, and chemistry. A society that builds its entire structure on the assumption of cheap, abundant, high EROI energy, and that fails to transition to alternative sources before the EROI of its primary source declines below a critical threshold, is in the same position as the Sumerians whose irrigation was driving salinization, or the Maya whose deforestation was degrading their soils. The physical reality has changed, but the social and economic structures have not adapted, and the gap between the two is where civilizational crises are born. There is another dimension to the energy question that deserves attention, and it relates to the concept of thermodynamic limits. The second law of thermodynamics states that in any energy transformation, some energy is inevitably lost as waste heat. No process is 100% efficient. Every time energy is converted from one form to another, from chemical to thermal, from thermal to mechanical, from mechanical to electrical, some portion is dissipated and becomes unavailable for useful work. This law is not a human invention. It is a fundamental feature of the physical universe. It cannot be engineered around. It cannot be legislated away. It cannot be overridden by market forces or political will. It is as inviolable as gravity. And it places absolute constraints on what any civilization can achieve with a given energy supply. A civilization that is growing, that is increasing its complexity, its population, its material throughput, is increasing its rate of energy consumption. And increasing energy consumption means increasing waste heat production. It also means increasing resource extraction, increasing waste generation, and increasing disruption of the natural systems that process and recycle those wastes. There is a fundamental thermodynamic limit to how much matter and energy a civilization can process on a finite planet before the waste products of that processing overwhelm the planet's capacity to absorb them. This is not a distant, theoretical limit. It is a limit that human civilization is now approaching in several dimensions simultaneously. The atmosphere's capacity to absorb carbon dioxide without undergoing significant warming is being approached or has already been exceeded. The ocean's capacity to absorb carbon dioxide without significant acidification is being approached. The freshwater cycle's capacity to sustain withdrawals at current rates is being exceeded in many regions. The soil's capacity to sustain current rates of erosion and nutrient depletion is being exceeded in many agricultural regions. The biosphere's capacity to absorb habitat loss and species removal without significant functional degradation is being exceeded. Each of these is a planetary limit, a boundary beyond which the system shifts to a new state, and each is being approached not because of any single cause, but because of the cumulative effect of a civilization operating at a scale and intensity that is testing the planet's capacity for self-regulation. We have now traced the operation of the planetary filter across multiple dimensions: soil, water, forests, climate, energy, and ecosystem function. We have seen it operate in ancient Mesopotamia, in the Maya lowlands, in the deserts of the ancestral Pueblones, in the forests surrounding Angkor, and in the frozen landscapes of Norse Greenland. We have seen how it interacts with the complexity of human societies, how it exploits the structural incentives that drive overexploitation, and how it manifests through tipping points that shift systems from one state to another. But there is one more dimension that must be addressed before we can fully appreciate the scope of the planetary filter, and it is perhaps the most important one: time. The Earth operates on timescales that are profoundly different from those of human societies. Geological processes unfold over millions of years. Soil formation occurs over thousands of years. Forest succession operates over centuries. Even the relatively rapid cycles of climate and weather operate on timescales that span decades or more. Human societies, by contrast, make decisions on timescales of years, election cycles, quarterly reports, annual budgets, and individual lifetimes. This mismatch in timescales is one of the most fundamental challenges of the human-Earth relationship. The consequences of actions taken today may not manifest for decades or centuries. The benefits of restraint exercised today may not be realized for generations. Human decision-making systems are not well designed to handle this kind of temporal disconnect. They are optimized for responding to immediate threats and opportunities, not for managing slow-moving, long-term processes. This temporal mismatch creates what might be called a slow trap. A civilization can degrade its environment for decades or centuries without experiencing significant consequences because the Earth's systems absorb the degradation. Each generation sees a world that appears to them to be functioning adequately. They have no experiential knowledge of the healthier state that existed before their time. They have no direct experience of the consequences that are building invisibly in the soil, the water, the atmosphere. By the time the consequences become apparent, by the time the feedback signal is strong enough to be unmistakable, the degradation may have progressed past the point where recovery is possible within any timeframe meaningful to human societies. This slow trap is compounded by the discounting of the future that is inherent in most human economic and political systems. A benefit received today is valued more highly than a benefit received in the future. A cost incurred today is weighted more heavily than a cost to be incurred in the future. This discounting is rational from the perspective of an individual with a finite lifespan, but it is catastrophic from the perspective of a civilization that must persist over centuries and millennia. It systematically undervalues long-term sustainability in favor of short-term gains, and it ensures that the slow trap remains largely invisible to the decision-making processes that determine a civilization's trajectory. Let us now draw together the threads of this first part of our exploration and consider what they mean, collectively, for our understanding of the relationship between human civilizations and the planetary systems on which they depend. The Earth is a complex, dynamic system governed by physical laws. It has feedback mechanisms that maintain conditions within certain ranges, but those ranges are not infinite. When external forces or internal disruptions push the system beyond its thresholds, it shifts to new states. These shifts are not gradual, they are abrupt, and they are not easily reversed. Human civilizations are also complex, dynamic systems. They grow by increasing their complexity, their specialization, and their resource consumption. This growth provides enormous benefits, but it also creates vulnerabilities. Complex societies are dependent on their resource base in ways that simpler societies are not. They are less flexible, less adaptable, and more susceptible to cascading failure when base-level resources are disrupted. The interaction between these two types of complex systems, human civilizations and planetary processes, creates the dynamic that we have been calling the planetary filter. Civilizations that maintain their resource consumption within the regenerative capacity of the systems they depend on can persist indefinitely, at least in principle. Civilizations that exceed that capacity enter a trajectory of degradation that leads, ultimately, to simplification, contraction, or collapse. The filter does not operate through judgment, intention, or design. It operates through physics, chemistry, and biology. It operates through the erosion of topsoil, the salinization of irrigated land, the depletion of aquifers, the loss of forest cover, the decline of fisheries, the acidification of oceans, the destabilization of climate, and the crossing of tipping points in ecosystems. It operates through the declining marginal returns on complexity, the falling energy return on investment, the tragedy of the commons, the shifting baseline syndrome, and the temporal mismatch between human decision-making and planetary processes. Every civilization in human history has been subject to this filter. Every civilization that has collapsed has, in some significant measure, been filtered by it. And every civilization that has endured has done so, at least in part, because it found ways to align its structures and practices with the physical constraints of the planet. This is not a comforting message. It is not a message of doom either. It is a message of constraint. The Earth does not negotiate. It does not make exceptions. It does not care about our aspirations, our ideologies, our economic theories, or our political systems. It responds to physical inputs with physical outputs. If we deplete the soil becomes less productive. If we drain the aquifers, the water runs out. If we cut the forests, the rain patterns change. If we saturate the atmosphere with greenhouse gases, the climate warms. These are not opinions. They are not theories. They are the operational characteristics of a physical system that has been functioning for 4.5 billion years. The question that confronts every civilization, including ours, is not whether the filter exists. It demonstrably does. The question is whether the civilization can perceive the filter, understand its mechanisms, and adjust its behavior accordingly before the feedback signals become catastrophic. And that question, the question of perception, understanding, and adaptation, is what we will explore in depth in the second part of this documentary. Before we continue to that second part, let us sit for a moment with the weight of what we have considered. We have looked at the deep history of the planet and seen how its systems operate, how they maintain balance, how they respond to disruption, and how they shift between states. We have looked at the history of human civilizations and seen the same patterns repeating across vastly different cultures, environments, and time periods. We have seen that the planetary filter operates not through malice but through mechanism, not through choice but through consequence. The civilizations that came before us were not less intelligent than we are. They were not less creative, less ambitious, less capable. Many of them understood, at least intuitively, that their relationship with their environment was the foundation of their prosperity. They developed laws to protect forests, customs to manage fisheries, traditions to preserve soil fertility, and rituals to honor the natural world on which they depended. And yet, again and again, the pressures of growth, competition, and short-term incentive overwhelmed these protections. The filter operated, the civilizations contracted, the planet continued. What is different now? What is different about the current moment in the long story of human civilization and its relationship with the Earth? That is the question we will take up when we continue. The answer, as we will see, is both hopeful and terrifying in equal measure. For the first time in human history, we have the tools to perceive the filter. We have the science to understand its mechanisms. We have the technology to measure our impact on the planet in real time. We have the knowledge to anticipate the consequences of our actions before they manifest. The question is whether we have the will. The question is whether we can translate knowledge into action, understanding into policy, awareness into transformation. The question is whether we can do what no civilization before us has done, consciously, deliberately, and systematically redesign our relationship with the planet to operate within its constraints rather than against them. The Earth is patient. It has been here for 4.5 billion years and will be here for several billion more. It has survived asteroid impacts, supervolcanic eruptions, complete glaciations, and atmosphere-altering biological revolutions. It will survive whatever we do. The question is not whether the Earth will continue. The question is whether our civilization will continue on it. The planet has seen many tenants come and go. Many species have risen to dominance and then vanished. Many ecosystems have flourished and then collapsed. Many climatic regimes have prevailed and then given way. The Earth does not mourn the passing of any of them. It simply moves on, reconfigures, and continues. We are the latest in a long line of experiments that the planet has run, not deliberately, but through the blind process of evolution and environmental interaction. We are extraordinary in many ways. We are the first experiment that is aware of itself, aware of the planet, aware of the filter. We are the first that has the capacity to understand its own situation and to choose a different path. But capacity is not destiny. Awareness is not action. Understanding is not transformation. Every civilization that has failed not because it lacked the capacity to change, but because it lacked the will, the structure, or the time. The soil beneath your feet is listening, not with ears. Not with consciousness, but with the patient, implacable responsiveness of a physical system that has been registering and responding to the actions of living things since the first microbe etched its mark on the first rock. It is registering your actions now. It is integrating the sum of every extraction, every emission, every disruption, and it will respond not with anger, not with judgment, but with physics, and physics does not forgive. We have journeyed through deep time, from the formation of the planet through the emergence of life, through the great extinctions, through the rise and fall of human civilizations, and through the mechanisms by which Earth systems respond to the pressures placed upon them. We have seen that the pattern of civilizational rise and decline is not random, not mysterious, and not morally determined. It is physically determined. It is the product of a complex interaction between human social systems and the planetary systems on which they depend. But our journey is only half complete. In the second part of this documentary, we will turn our attention to the present and the future. We will examine the specific ways in which our current global civilization is interacting with planetary systems, the feedback signals we are receiving, and the choices that lie before us. We will explore the concept of planetary boundaries, the framework that scientists have developed to identify the safe operating space for humanity within the Earth system. We will examine the dynamics of energy transition, the challenges of complexity management, and the possibilities for redesigning our civilizational structures for resilience rather than growth. We will ask and attempt to answer the question that has haunted every civilization but that only ours has the knowledge to ask with full awareness. Can we change course before the filter claims us? The Earth does not care about our answer, but we should. That is where we will pause for now. The ground beneath us holds the records of those who came before, written in buried foundations and abandoned fields, in eroded hillsides and salinized plains, in dried lake beds and silted reservoirs. Those records tell a consistent story, a story of civilizations that grew beyond their means and were answered by the planet they depended on. The question is not whether we can read those records. We can. The question is whether we will heed them. Join us for the second part of this documentary, where we will take everything we have learned from the past and apply it to the challenge that confronts us now. The challenge of building a civilization that the Earth does not filter out, a civilization that operates not against the planet but in concert with it, a civilization that does not merely survive but endures. The planet is waiting, it always has been, and it always will be. We left the first part of this documentary standing at the edge of a long and sobering history. We had traveled through deep time, through the mechanics of planetary systems, through the ruins of civilizations that had been answered by the Earth they depended on. We had seen the filter operate in deserts that were once fertile plains, in jungles that had swallowed great cities, in frozen coastlines that had consumed the last remnants of colonies that refused to adapt. We had traced the mechanisms, the feedback loops, the tipping points, the declining returns on complexity, the tragedy of the commons, the slow trap of temporal mismatch. We had established, through history and through science, that the planetary filter is real, that it is mechanical, and that it is indifferent. Now we turn to the present. Not to a catalog of current problems, not to a list of today's crises, but to the deeper question of what our particular moment in civilizational history means in the context of everything we have explored. We live in an era unlike any that has preceded it, not simply because of our technology or our population or our global connectivity, but because of something far more consequential. We are the first civilization in the history of life on this planet that is aware of the filter. We can measure it, we can model it, we can trace its operation in real time. We can project its future behavior with a degree of precision that would have been unimaginable even a century ago. That awareness is both our greatest asset and our most profound burden. It is our greatest asset because it means that, for the first time, a civilization has the capacity to perceive the feedback signals of the planetary system before they become catastrophic, to understand the mechanisms of its own potential undoing, and to choose a different path. It is our most profound burden because awareness without action is merely a more sophisticated form of the same failure that claimed the civilizations before us. The Maya had priests who read the sky and scribes who recorded the harvests and rulers who understood that the land was being worked too hard. The Sumerians had record keepers who documented declining yields. The Norse in Greenland could see with their own eyes that the pastures were shrinking and the sea ice was advancing. Awareness alone did not save them. What would it take for awareness to be different this time? What would it take for understanding to become transformation? That is the question that will occupy us for the remainder of this documentary. Please be sure you have subscribed to the channel and let us continue the journey. To begin to answer that question, we must first understand what is genuinely different about the current situation, not in terms of specific problems, but in terms of the structural dynamics that govern the relationship between our civilization and the planet. The most important structural difference is one of scale. Every previous civilization that encountered the planetary filter did so within a geographically bounded context. The Sumerians degraded the soils of southern Mesopotamia. The Maya disrupted the hydrology of the Yucatan lowlands. The Khmer altered the water cycles of the Cambodian floodplain. Each of these was significant. Each had consequences that extended beyond the immediate territory. But each was, in the final analysis, a regional interaction between a human society and a regional set of planetary systems. The rest of the planet was unaffected. When the society collapsed, the systems it had disrupted eventually recovered, slowly but inexorably, and other life, human and otherwise, moved in to occupy the space. Our current civilization is different in a way that is qualitative rather than merely quantitative. It is not simply larger, it is global. Its interactions with planetary systems are not regional, they are planetary in scope. The carbon dioxide that is added to the atmosphere by human activities does not stay over the region where it was emitted. It disperses throughout the global atmosphere within years and affects the climate of every region on the planet. The nitrogen and phosphorus from agricultural fertilizers that wash into rivers and eventually into the ocean do not affect only local coastal ecosystems. They affect the chemistry and productivity of the global ocean. The freshwater extracted from river systems and aquifers to supply agricultural and urban demands does not affect only local water tables. It alters regional and global water cycles. The habitats cleared for agriculture and development do not affect only local biodiversity. They reduce the global diversity of life and disrupt the ecosystem functions that stable biodiversity provides at the planetary level. For the first time in the history of human civilization, a single civilization is interacting with the Earth systems at a scale that matches the scale of those systems. This changes everything about the dynamics of the planetary filter. In previous instances, when a civilization collapsed under the weight of its environmental impact, the damage was localized. The filter operated regionally. Other regions were unaffected. Life, including human life, continued elsewhere. The planet had buffers. The global system was much larger than any regional civilization, and so the regional degradation, however catastrophic for those who experienced it, did not destabilize the global system. There are no such buffers left for a global civilization. If our civilization interacts with the Earth systems in ways that destabilize them, there is no other region, no unaffected elsewhere, to absorb the impact or to serve as a refuge. The filter, if it operates on our civilization, will operate at the planetary scale. That is a fundamentally different situation from any that human civilization has previously faced, and it requires a fundamentally different level of understanding and response. This global scale of interaction brings us to the concept of planetary boundaries, a framework developed by Earth system scientists that attempts to define the safe operating space for human civilization within the Earth system. The framework identifies a set of key Earth system processes that regulate the overall state of the planet, and for each one, attempts to identify a threshold beyond which the process is at risk of shifting to a significantly different state, one that might be far less hospitable to human civilization. The concept is not about identifying the precise moment of catastrophe. Complex systems do not usually fail at precisely defined thresholds. The framework is about identifying zones of uncertainty, regions of parameter space where the risk of triggering large-scale, potentially irreversible shifts begins to increase significantly. Think of it less like a cliff edge and more like a slope that gradually steepens. For a while, you can walk on it safely. As you move further along, the ground becomes less stable and the risk of slipping increases. Eventually, you reach a point where the risk of a fall becomes so high that continuing to move in the same direction is clearly unwise, even if you cannot identify the exact step that will trigger the fall. The planetary boundaries framework identifies processes including climate regulation, the integrity of the biosphere, the cycling of nitrogen and phosphorus, freshwater use, land use change, ocean acidification, the depletion of stratospheric ozone, the loading of novel entities such as synthetic chemicals and plastics into the environment, and the loading of aerosols into the atmosphere. Each of these represents a dimension along which human activity is pushing the Earth system. Each has a boundary beyond which the risk of large-scale disruption increases significantly. What is striking about this framework, and what makes it so relevant to our discussion, is that it makes explicit the concept of operating space. Every civilization operates within a space defined by the constraints of the planetary systems it depends on. For most of human history, that space was so much larger than the scale of civilization that the constraints were effectively invisible. The space appeared infinite because civilization was small relative to the space. As civilization has grown, the space has appeared to shrink, not because the absolute limits have changed, but because our occupation of the available space has expanded dramatically. Understanding the planetary boundaries framework is not about accepting doom. It is about mapping the territory. A cartographer who maps the coastline is not condemning sailors. The cartographer is providing the information necessary for navigation. The planetary boundaries framework is an attempt to map the coastline of human civilization's operating space, to identify where the safe harbors are and where the reefs lie. Navigation without this map is not bravery, it is blindness. Consider now the concept of resilience and how it differs from the concept of robustness that has governed most human thinking about civilizational design. Robustness is the ability to resist disturbance. A robust structure maintains its integrity in the face of stresses. A robust bridge carries the expected loads without deforming. A robust fortress withstands the expected attacks without breaching. A robust economy maintains its output in the face of expected shocks. Robustness is a valuable quality, but it is a quality that is defined relative to a specific set of anticipated stresses. A structure that is robust against the stresses it was designed to handle may be brittle against stresses it was not designed to handle. Resilience is different. Resilience is the ability to absorb disturbance and reorganize while undergoing change so as to retain essentially the same function, structure, identity, and feedbacks. A resilient system is not one that never changes. It is one that can change without losing its essential character, one that can flex and absorb and adapt without shattering. Resilience is not defined relative to a specific set of anticipated stresses. It is a general capacity that allows a system to navigate a wide range of unforeseen challenges. The distinction between robustness and resilience is crucial because the planetary filter does not operate only through anticipated stresses. It operates through the full range of variability that the Earth system can generate, including rare, extreme events that no civilization could specifically anticipate. An El Niño that brings drought to one region and flooding to another. A volcanic eruption that disrupts global temperatures for several years. A pandemic that eliminates a significant fraction of the population. A prolonged solar minimum that reduces agricultural productivity. These events are unpredictable in their timing and their specifics, but they are entirely predictable in the sense that they will occur. The Earth system generates variability. It always has and always will. A civilization that is designed for robustness against specific, anticipated stresses is vulnerable to the unexpected. A civilization that is designed for resilience has a much better chance of surviving whatever the planet sends because it can adapt, it can reorganize, it can absorb shock without shattering, because it has not sacrificed flexibility in the pursuit of optimal performance in a specific expected environment. The failure mode of robustness-focused civilizational design is precisely the failure mode we have seen repeatedly in our historical examples. The great irrigation systems of Mesopotamia were extraordinarily robust against drought, but they were brittle against the secondary effect of salinization, an effect that was not anticipated in the design of the system. The Maya water management systems were remarkably robust for the average conditions of the Classic period, but they were brittle against the combination of environmental degradation and climatic variability that struck in the 9th century. The Khmer hydraulic system was an engineering marvel, robust against the normal variability of the monsoon, but brittle against the combination of infrastructure decay and the more erratic rainfall patterns of the 14th and 15th centuries. In each case, the civilization had optimized its systems for performance under expected conditions. The optimization came at the cost of adaptability. The systems were complex, specialized, and efficient, but they were not flexible. And when conditions departed from the expected, the systems could not adapt. The filter operated. Resilience requires diversity. In ecological systems, the resilience of an ecosystem is strongly related to its biodiversity. More species means more functional redundancy, more ways for the ecosystem to maintain its processes even when individual components are lost or stressed. A forest with 300 tree species is more resilient than one with 3 species, because if a disease or a drought preferentially affects 1 or 2 species, the others can continue to maintain the ecosystem's overall function. A monoculture, by contrast, is maximally vulnerable to any stress that specifically affects the crop in question. The Irish potato famine of the 1840s is the paradigmatic example. A population that had become almost entirely dependent on a single crop variety had no resilience against the fungal disease that destroyed it. The famine that resulted was not merely a natural disaster. It was the product of a civilizational system that had sacrificed diversity and resilience for productivity and simplicity. The lesson applies equally to human social and economic systems. A society that is heavily dependent on a single crop, a single energy source, a single trade partner, a single supplier of a critical resource, is structurally vulnerable in ways that a more diversified society is not. The diversity of sources, methods, pathways, and solutions is what gives a system the capacity to adapt when one component fails. And in a world where the Earth system generates constant variability and occasional extreme disruptions, adaptability is not a luxury. It is a survival requirement. We have established that the planetary filter operates through the degradation of the resource base on which civilizations depend, and that this degradation is driven by extraction that exceeds the regenerative capacity of the systems being exploited. We have established that the filter is indifferent, mechanical, and physical. We have established that complexity creates vulnerability as well as capability. And we have established that resilience, not robustness, is the quality that allows civilizations to navigate the full range of planetary variability. Now let us turn to a question that is central to everything we have been discussing. What is the mechanism by which civilizations either find their way to sustainability or fail to do so? What determines whether a civilization manages to operate within the regenerative limits of its environment or whether it overshoots and collapses? The answer in its most fundamental form is governance. Not any particular form of governance, not any specific political system, ideology, or institution, but governance in the broadest sense. The set of mechanisms by which a society collectively manages its relationship with the shared resources and systems on which it depends. Governance, in this sense, is the feedback mechanism that translates environmental signals into social responses. A society with effective governance perceives changes in its resource base, correctly interprets the significance of those changes, and adjusts its behavior accordingly. A society with ineffective governance fails at one or more of these steps. It fails to perceive the signals, or it perceives them but misinterprets their significance, or it correctly interprets them but lacks the mechanisms to translate that understanding into effective collective action. The history of civilizational collapse can be read in part as a history of governance failure. Not in the narrow political sense of corruption or incompetence, though these are certainly present, but in the deeper sense of a failure of the social feedback mechanisms that connect environmental reality to human behavior. When the connection between environmental degradation and social consequences is clear, immediate, and directly experienced by the decision makers, governance tends to work better. When the connection is indirect, delayed, or experienced primarily by people without power, governance tends to fail. This is why commons management at the community level has often been more effective than governance at larger scales. When a village manages a shared forest, the people who make the rules about how much timber can be cut are the same people who depend on the forest for their fuel, their building materials, and their protection against erosion. The feedback between governance decisions and environmental consequences is direct and immediate. The decision makers feel the consequences of their own decisions. This alignment of decision-making authority with the experience of consequences is one of the most important factors in effective environmental governance. As societies grow larger and more complex, this alignment tends to break down. Decision-makers become insulated from the environmental consequences of their decisions by distance, wealth, and political power. The farmer who manages a small plot of land feels the effects of soil degradation immediately. The administrator who manages agricultural policy for a large region may never see the fields whose fate they determine. The misalignment between authority and consequence creates a structural tendency toward mismanagement, not because the administrators are bad people, but because they are not receiving the feedback signals that would guide good decisions. Effective large-scale governance of shared resources requires institutional mechanisms that compensate for this misalignment. Monitoring systems that generate accurate information about resource condition, transparency mechanisms that make that information available to decision makers, and to the public accountability structures that connect decision makers' fates to the outcomes of their decisions, and enforcement mechanisms that prevent the short-term interests of powerful individuals from overriding the long-term interests of the collective. These are not easy problems. They are among the hardest problems in political science, economics, and public administration. But they are not impossible. The history of successful long-term resource management provides examples of societies that have solved these problems, at least partially and at least for significant periods of time. The irrigation systems of Bali, managed through a complex web of water temples and traditional governance structures, have maintained sustainable rice production for over 1,000 years. The mountain commons of the Alps, managed by village communities under elaborate traditional rules, have maintained forest cover and pasture quality for centuries. The fisheries governance systems of various Pacific Island cultures maintained sustainable fish populations for generations. None of these are perfect solutions. All have faced pressures and have evolved over time. But all demonstrate that sustainable governance of shared resources is possible, and all share certain common features. Clear rules about resource use, effective monitoring of resource condition, graduated sanctions for rule violations, and mechanisms for conflict resolution. What we can draw from the historical record of both successful and unsuccessful governance is a set of principles that appear to be associated with civilizational persistence. These are not rules in any prescriptive sense. They are observations about the features that distinguish societies that managed to maintain themselves within the constraints of their resource base from those that did not. The first principle is measurability. Societies that managed their resources sustainably were almost universally societies that actively measured the condition of the resources they depended on. They counted fish, they tracked water levels, they monitored soil quality, they observed the condition of their forests, they paid attention. The act of measurement is not merely informational, it is institutional. It creates a feedback loop. It connects the present condition of the resource to the present awareness of the society. Without measurement, degradation remains invisible until it is too late. With measurement, the early signals of stress can be perceived and addressed before they become critical. The second principle is the alignment of decision-making timescales with resource recovery timescales. This is one of the hardest problems in civilizational governance, but it is also one of the most important. Resources recover on their own timescales, and those timescales often extend far beyond any human institution's natural planning horizon. A forest takes decades to regenerate after heavy cutting. A fishery takes years to recover from overfishing. An aquifer takes thousands of years to recharge. A soil takes centuries to rebuild its organic matter and microbial communities after severe degradation. Governance systems that evaluate success and failure on annual or decadal timescales will systematically undervalue long-term resource maintenance and systematically overvalue short-term extraction. Successful resource governance systems have often incorporated mechanisms to extend the effective planning horizon of decision makers. Long-term land tenure, which gives farmers a stake in the future productivity of their land rather than just the current crop, is one such mechanism. Cultural traditions that encode knowledge about resource management across many generations are another. Religious and ethical frameworks that place obligations to future generations or to the natural world itself can serve as proxies for long-term governance when institutional mechanisms fail. The third principle is diversity and redundancy. Societies that survived environmental variability were societies that maintained diversity in their food sources, their water supplies, their energy sources, their trade relationships, and their social structures. They did not put all of their resources into a single basket. They maintained backup systems, alternative pathways, and reserve capacity that could be activated when primary systems failed. This redundancy was often economically inefficient in normal times. A society that maintains 3 different crops, each adapted to slightly different conditions, is not as productive as one that grows only the highest yielding crop in optimal conditions. But when conditions become suboptimal, or when a pest or disease strikes the single crop, the diversified society has options. The specialized society does not. The fourth principle is adaptive capacity. The civilizations that endured were not those that found the optimal solution to their environmental challenges and maintained it unchanged forever. They were those that continuously refined and adapted their solutions as conditions changed. The Balinese water temple system has evolved over 1,000 years, incorporating new rice varieties, responding to changes in pest populations, adapting to changes in water availability. It is not a static solution. It is a dynamic one with built-in mechanisms for monitoring, feedback, and adjustment. The capacity for adaptation is itself a resource, and it is one that must be cultivated and maintained. The fifth principle is social cohesion and cooperation. Environmental governance requires collective action. It requires individuals to subordinate short-term personal interests to long-term collective ones. This is not possible without some level of social trust, shared identity, and commitment to collective welfare. Societies with high levels of internal conflict, extreme inequality, or weak social bonds are less capable of maintaining the collective governance of shared resources. They are more vulnerable to the tragedy of the commons because the mechanisms that can prevent it, social norms, community pressure, collective monitoring, and enforcement, are weaker in more fragmented societies. This is not to say that equality is a sufficient condition for sustainable governance. Many highly egalitarian societies have still collapsed under environmental stress, but extreme inequality, of the kind that insulates the wealthy from the consequences of environmental degradation while concentrating the costs among the powerless, is a consistent feature of societies that fail to address environmental challenges in time. When the people who bear the costs of degradation have no political voice, the feedback loop between environmental reality and governance decision is broken. Let us now consider the relationship between energy systems and civilizational resilience, because this relationship is one of the most important and least understood dimensions of the planetary filter. We established in the first part of this documentary that every civilization requires energy, and that the sustainability of a civilization is intimately connected to the sustainability of its energy supply. The EROI, the energy return on investment of the primary energy source, determines how much surplus energy the civilization has available for all the activities that constitute civilizational life beyond the mere securing of energy itself. But there is another dimension of energy systems that is equally important for resilience, and it is the dimension of distribution. Not just how much energy is available, but how that energy is distributed through the system. A highly centralized energy system, in which energy is produced at a small number of large facilities and distributed through an extensive grid or pipeline network to millions of end users, has very different resilience characteristics than a decentralized system in which energy is produced at many small, distributed locations close to the points of use. The centralized system is efficient in normal operation. It benefits from economies of scale. It requires less total installed capacity to meet a given level of demand, but it is brittle in the face of disruption. A failure at a central production facility can deprive vast numbers of users of energy simultaneously. A failure in the distribution network can have the same effect. The more centralized the system, the greater the potential impact of any single point of failure. The decentralized system is less efficient in normal operation. It requires more total installed capacity and more complex local management, but it is far more resilient in the face of disruption. A failure in one distributed production facility affects only the local area it serves. The rest of the system continues to function. The failure does not cascade. The system can absorb the loss of individual components without losing overall function. This distinction between centralized efficiency and decentralized resilience is one of the fundamental trade-offs in the design of any complex system. And it is a trade-off that every civilization must navigate in designing its energy, food, water, and other critical infrastructure systems. Optimizing for efficiency tends to produce centralized, specialized systems that are highly productive under normal conditions but brittle under stress. Optimizing for resilience tends to produce decentralized, diversified systems that are somewhat less productive under normal conditions but far more capable of maintaining function under stress. The history of civilizational collapse suggests that the bias toward efficiency at the expense of resilience is one of the most consistently dangerous features of complex societies. As civilizations grow and specialize, they tend to concentrate their critical systems, their water supplies, their food production, their energy generation into fewer, larger, more efficient units. Each step in this process seems rational in isolation. The large centralized irrigation system produces more food per unit of labor than many small independent water sources. The large specialized farm produces more food per unit of land than many small diversified farms. The large centralized power station produces more energy per unit of capital than many small distributed generators. But each step also increases the system's vulnerability to disruption, because each step reduces redundancy, reduces diversity, and increases the number of people and activities that depend on any single component. The tension between efficiency and resilience is not resolvable through a single optimal design. It is a permanent tension that must be managed through ongoing governance. The challenge is to capture enough of the benefits of efficiency to support high levels of civilizational function while maintaining enough resilience to survive the range of variability that the Earth system generates. This requires not just technical design choices but institutional ones, governance mechanisms that actively monitor the system's resilience and intervene when efficiency optimization has proceeded too far at resilience's expense. There is a concept in ecology that is deeply relevant here, and it is worth taking some time to explore. The concept is called the adaptive cycle, and it was developed by the ecologist C.S. Holling and his colleagues as a way of understanding the dynamics of complex adaptive systems over time. The adaptive cycle describes the trajectory of complex systems through 4 phases. The first phase is the growth or exploitation phase, in which resources are abundant and the system expands rapidly, with high connectivity and high productivity but low resilience. The second phase is the conservation phase, in which the system reaches maturity and becomes increasingly rigid and efficient, with resources locked up in existing structures and less available for novelty and adaptation. The third phase is the release or collapse phase, in which accumulated vulnerabilities lead to a rapid breakdown of the existing structure, releasing the resources that had been locked up. The fourth phase is the reorganization phase, in which the released resources are available for new combinations and experiments, and the system explores new configurations before beginning the growth phase again. This cycle operates at multiple scales simultaneously, from the scale of individual organisms to the scale of entire ecosystems, and from the scale of individual economic enterprises to the scale of entire civilizations. At each scale, the system moves through growth, conservation, release, and reorganization. And at each scale, the release phase, which from within the system looks like catastrophic collapse, is also the precondition for reorganization and renewal. The forest fire that seems to destroy the forest is also the event that releases the nutrients locked in the standing biomass and creates the conditions for new growth. The collapse of an overextended civilization that seems to destroy all that was built is also the event that releases the social, cultural, and material resources for new configurations to emerge. This is not a comforting framework in the sense of making collapse seem acceptable or desirable. From the perspective of the people who live through a collapse phase, it is a catastrophe. People suffer, lives are destroyed, knowledge and culture are lost. The suffering is real and significant. But from the perspective of the long-term trajectory of complex adaptive systems, collapse is not the end. It is a phase, a painful and sometimes prolonged phase, but a phase nonetheless, one that contains within it the seeds of what comes next. The adaptive cycle also suggests something important about the relationship between scale and timing. Collapses at smaller scales can be absorbed by the larger systems in which they are embedded, and they provide the raw material for innovation and renewal at those larger scales. But if collapse occurs simultaneously at multiple scales, if the local, regional, and global systems are all in the release phase at the same time, the reorganization phase becomes far more difficult and far less certain to produce viable new configurations. This is why the global scale of our current civilization's interaction with planetary systems is so significant. Previous civilizations collapsed at regional scales. Their collapse released resources and knowledge that were absorbed by surviving civilizations at larger scales. The knowledge of Greek civilization was preserved and extended by the civilizations that followed. The agricultural techniques of collapsed pre-Columbian civilizations survived in adapted forms in communities that endured. The release phase of regional civilizations fed the reorganization phase of the global system in which they were embedded. If a civilization operating at the global scale were to enter a release phase, there is no larger system in which that collapse could be absorbed and from which renewal could come. The reorganization would have to occur at the same scale as the collapse. That is not impossible. Complex systems do reorganize after global scale collapses. The Earth has reorganized after every mass extinction, but the timescale of reorganization is proportional to the scale of the collapse. Regional civilizations reorganize over decades to centuries. Global civilizations, if they were to collapse, would reorganize over centuries to millennia, and the suffering in the interim would be on a scale that is difficult to comprehend. Let us now turn to the question of knowledge and its role in the relationship between civilizations and the planetary filter. We have said that our civilization is unique in its awareness of the filter, but what does this awareness actually consist of, and what are its limits? Human knowledge of Earth systems has advanced dramatically over the past several centuries, and especially in the past several decades. We now have satellite systems that monitor the planet's surface, oceans, and atmosphere in near real time. We have networks of measuring stations that track temperature, precipitation, atmospheric composition, ocean chemistry, ice extent, and dozens of other variables continuously. We have computer models that simulate the dynamics of the Earth system with a degree of sophistication that allows us to project future conditions with reasonable confidence across a range of scenarios. We have a vast scientific literature that synthesizes these observations and projections into an increasingly coherent picture of how the Earth system works and how it is responding to human activity. This knowledge is genuinely extraordinary. No previous civilization had anything approaching this level of understanding of the planetary systems on which it depended. The Sumerians had no way to measure the rate of salinization of their agricultural soils. The Maya had no way to project the future trajectory of deforestation in their region. The Greenland Norse had no way to understand the climatic changes that were making their way of life untenable. We have all of these capacities and more, but knowledge has limits that are important to understand, because they are limits that cannot be overcome simply by generating more data or building better models. The first limit is complexity. The Earth system is extraordinarily complex, with more interacting components, feedback loops, and nonlinear dynamics than any model can fully capture. Our models are good, but they are simplifications. They capture the major dynamics but miss many of the details, and in complex systems, details matter. A small difference in a feedback parameter can, under the right conditions, produce dramatically different outcomes. The uncertainty in our projections of future Earth system states is not a failure of science. It is an inherent feature of the system we are trying to model. The second limit is surprise. Complex systems can produce outcomes that are genuinely novel, outcomes that do not emerge from any prior pattern and that therefore cannot be anticipated by any model based on historical data. The tipping points we discussed earlier are examples of this kind of surprise. A system can approach a tipping point without showing clear signs of imminent transition and then cross it suddenly and irreversibly. The warning signals exist in principle, but they may be subtle and easily masked by normal variability. We may have more warning than the civilizations before us, but we do not have certainty. The third limit is the gap between knowledge and action. Even if we know exactly what is happening to the Earth's systems, and even if we know exactly what changes in human behavior would be necessary to prevent harmful thresholds from being crossed, that knowledge does not automatically translate into the collective action necessary to change behavior at the required scale. The mechanisms of governance, culture, economics, and politics that mediate the relationship between knowledge and action are themselves complex systems with their own dynamics, their own inertias, their own tipping points, and their own uncertainties. This gap between knowledge and action is perhaps the most critical challenge facing our civilization. It is the challenge that most directly determines whether our awareness of the planetary filter will prove to be our distinguishing advantage, or simply our most eloquent witness to our own undoing. Understanding the gap between knowledge and action requires understanding something about how social change actually occurs, and how civilizations manage to make transitions of the kind that our current situation appears to require. Social change is not primarily driven by the rational processing of information by individuals. If it were, the history of human civilization would look very different. Societies would have recognized environmental degradation more consistently, responded to early warning signals more reliably, and avoided the boom and bust cycles that have characterized so much of human civilizational history. The fact that they did not demonstrates that rational information processing is not the primary driver of social behavior, even in societies with sophisticated knowledge systems. Social change is driven by a complex interaction of economic incentives, cultural narratives, power structures, technological possibilities, and the kind of sudden shift in shared understanding that sociologists call a tipping point in social norms. Just as physical systems have tipping points beyond which they shift abruptly to new states, social systems have tipping points at which dominant patterns of behavior, belief, and institution can shift rapidly and fundamentally. The history of major social transitions illustrates this dynamic. The abolition of practices that were once considered normal and natural by the societies that practiced them has occurred repeatedly through human history, often with surprising speed once a tipping point in social norms was reached. The transition from one energy system to another, the shift from wood to coal, from coal to oil, has historically occurred far faster than any rational analysis of the relative merits of the two systems would have predicted, because the transition was driven not by rational optimization, but by a combination of economic incentives, technological breakthroughs, entrepreneurial energy, and shifting cultural narratives about progress and modernity. This suggests that social systems can change rapidly, faster than the slow accumulation of rational argument would imply. But it also suggests that the direction and character of that rapid change is not easily controlled. Social tipping points, once triggered, can produce changes that go far beyond what any particular actor intended or planned. They can produce unintended consequences, secondary effects, and new dynamics that were not visible from within the old system. Understanding this dynamic has important implications for how we think about the transition that our civilization appears to need. A transition from a model of perpetual growth in material throughput to a model of sustainable operation within planetary boundaries. Such a transition is not simply a matter of making better rational choices. It requires a shift in the economic incentives that govern individual and corporate behavior, a shift in the cultural narratives that define what success and progress mean, a shift in the technological systems that mediate the relationship between human activity and natural systems, and a shift in the governance mechanisms that determine how shared resources are managed. Each of these shifts is individually difficult. Together, they constitute a transformation of civilizational scale. Whether such a transformation is achievable within the timeframe available, before the planetary filter reaches the critical thresholds that would force a far more disruptive form of change, is one of the most important open questions in the history of our species. Let us think more carefully about what a civilization designed for resilience and sustainability would look like, not in terms of specific technologies or policies, but in terms of its fundamental structural principles. What are the architectural features of a civilization that could persist over the long term within the constraints of a finite planetary system? The first principle is material circularity. A civilization that extracts resources from the environment, processes them into goods, uses those goods, and then discards the resulting waste is a civilization that depends on an ever-expanding supply of new resources and an ever-expanding capacity to absorb waste. On a finite planet, neither of these expansions can continue indefinitely. A civilization designed for long-term persistence must close the loops. The materials and products must be recoverable and reusable. The nutrients in food must cycle back to the soil. The waste heat of industrial processes must be captured and used. The organic matter and biological waste must be composted and returned to ecosystems. Material circularity is not just an environmental virtue. It is a physical requirement for long-term civilizational sustainability. The concept of material circularity is not novel. Nature has practiced it for billions of years. Every ecosystem is a circular economy. The waste of one organism is the resource of another. Nutrients cycle through the system continuously, from soil to plant to herbivore to predator to decomposer and back to soil. There is no concept of waste in a functioning ecosystem, only resources in transit. The challenge for human civilization is to redesign its material systems to operate on the same principle, to treat materials as assets to be cycled rather than inputs to be consumed and discarded. This is an enormous engineering challenge. The material systems of modern civilization are extraordinarily complex and deeply embedded in the physical infrastructure of our societies. Changing them requires not just technological innovation but institutional redesign, changes in the rules and incentives that govern how materials flow through the economy. But it is a challenge that has, in many domains, already been partially addressed. Recycling, composting, remanufacturing, and the recovery and reuse of industrial materials are all examples of circular material flows that already exist, at various scales, in modern economies. The question is not whether material circularity is possible, but whether it can be extended to all material flows at the scale and speed that physical planetary constraints require. The second principle is energy quality and flow rate management. A civilization's energy system must not only be sustainable in its source, but also in its rate of consumption. Even a fully renewable energy system has limits imposed by the laws of thermodynamics and by the finite surface area and resource requirements of renewable energy infrastructure. Solar panels require materials. Wind turbines require materials. These materials must be extracted, processed, and eventually recovered and recycled. The total material throughput of a renewable energy system is far less than that of a fossil fuel system per unit of energy delivered, but it is not zero. A civilization that consumes renewable energy at an ever-increasing rate will eventually encounter limits imposed by the availability of the materials needed to build and maintain the renewable infrastructure. Managing energy flow rates is therefore as important as managing energy sources. This does not necessarily mean reducing the quality of life experienced by the population. Many activities that consume large amounts of energy in current civilizational systems consume far more than they need to deliver their essential function, due to inefficiencies in design, operation, and infrastructure. The amount of energy required to maintain comfortable indoor temperatures in a well-designed and well-insulated building is far less than in a poorly designed one. The amount of energy required to transport people and goods in a well-designed urban system is far less than in a system designed primarily around the private automobile. The amount of energy embedded in the food supply is far more than necessary when food systems are designed around long supply chains, high-input agriculture, and substantial waste. Efficiency improvements in these areas can deliver the same or better quality of service with dramatically less energy, creating the possibility of maintaining civilizational function at lower total energy consumption. The third principle is ecological integration. A civilization designed for long-term persistence must integrate with the ecological systems of the planet rather than simply extracting from them or displacing them. This means maintaining sufficient natural habitat to sustain the ecosystem functions, pollination, water purification, climate regulation, nutrient cycling, and soil formation that human civilization depends on. It means managing agricultural systems in ways that maintain rather than degrade soil health, water quality, and biodiversity. It means designing urban systems that incorporate natural processes rather than replacing them with engineered substitutes. And it means recognizing that the value of intact natural systems to human civilization is not primarily aesthetic or recreational but functional, the delivery of services that are essential to civilizational operation and extraordinarily expensive to replace with technological alternatives. The concept of ecological integration goes beyond the preservation of specific species or habitats. It involves understanding the functional relationships between human systems and natural systems and designing the former to support rather than undermine the latter. This requires a level of understanding of ecological dynamics that is only now becoming available through the advances in ecological science of the past several decades. It also requires a cultural shift in how human civilization understands its relationship to the natural world, a shift from the conception of nature as a resource to be exploited to the conception of nature as a partner and a foundation without which civilizational function is impossible. Now let us examine the concept of what might be called civilizational metabolism, because this concept brings together many of the themes we have been discussing in a way that clarifies both the challenge and the possibilities. Every organism has a metabolism, a set of processes by which it takes in energy and matter from its environment, converts them into the structures and activities that constitute its life, and releases waste products back into the environment. The rate of metabolism determines the organism's demands on its environment. An organism with a very high metabolic rate must consume more food, breathe more oxygen, and produce more waste than an organism with a lower metabolic rate. If the supply of food and oxygen is limited, the high metabolism organism will either consume its environment faster than it can regenerate or will die. Civilizations have metabolisms too. They take in energy and matter from their environments, convert them into the structures and activities that constitute civilizational life, and release waste products back into the environment. The rate of civilizational metabolism, measured as the total flow of energy and matter through the civilization per unit time, determines the civilization's demands on its environment. A civilization with a very high metabolic rate demands more from the environment than one with a lower metabolic rate. The Earth can support different levels of civilizational metabolism depending on how efficient the civilization is in its use of energy and matter, and how closely the waste products of civilizational metabolism match the inputs that Earth's recycling systems can process. A civilization that uses energy and matter very efficiently, that produces waste in forms and at rates that Earth systems can absorb and recycle, can sustain a higher metabolic rate than one that is profligate with its resources and whose wastes overwhelm the planet's absorptive capacity. The critical insight is that civilizational metabolism can be either aligned or misaligned with the planet's capacity to supply resources and absorb wastes. A civilization in metabolic alignment with the planet can persist indefinitely because its demands do not exceed supply and its wastes do not exceed the planet's capacity to process them. A civilization in metabolic misalignment is an overshoot. It is consuming its own capital, degrading the resource base that supports it, and accumulating wastes faster than the planet can recycle them. Eventually, as we have seen repeatedly in the historical record, overshoot is corrected. But the correction often comes in the form of collapse rather than voluntary adjustment. The challenge of civilizational sustainability is, at its most fundamental level, the challenge of bringing civilizational metabolism into alignment with planetary capacity. This does not require returning to pre-industrial levels of technology or human welfare. It requires designing civilizational systems, the systems of food production, energy generation, material processing, water management, and waste handling, to operate within the regenerative and absorptive limits of the planetary system. This is a design problem, a governance problem, a technology problem, and a cultural problem simultaneously. One of the most profound lessons from the history of civilizational collapse is the danger of what we might call the complexity trap, and it deserves extended treatment because it is one of the most counterintuitive aspects of the relationship between civilization and the planetary filter. As we discussed in the first part of this documentary, civilizations tend to respond to problems by increasing their complexity. Each increase in complexity provides a solution to the immediate problem, but also increases the energy and resource demands of the civilization, reduces its flexibility, and adds new potential points of failure. As complexity increases, the cost of maintaining it increases. As the cost of maintaining it increases, the civilization must work harder to sustain its existing level of function. Less surplus is available for investment, for innovation, for resilience building. The civilization becomes increasingly focused on maintaining what it has rather than adapting to what is coming. This is the complexity trap. The civilization is too complex to simplify without catastrophic loss of function, but too energy-intensive to maintain without continuous high resource inputs. It is trapped between the complexity it cannot give up and the resources it can no longer count on. The trap closes as resources decline and complexity increases simultaneously, and the civilization finds itself with less and less room to maneuver. History suggests that civilizations in the complexity trap tend to respond to resource stress in ways that deepen rather than resolve the trap. They add new layers of administration to manage the complexity. They launch military campaigns to secure new resources. They implement new technologies to extract resources more efficiently from existing sources. They increase the specialization of their workforce to improve productivity. Each of these responses is locally rational. Each temporarily relieves the immediate stress, but each also increases the civilization's complexity, energy demands, and resource dependence. The temporary relief comes at the cost of long-term resilience. The only way to escape the complexity trap is through a process of deliberate simplification, the voluntary reduction of complexity to levels that can be maintained on a sustainable resource base, while retaining the elements of complexity that are most essential to human welfare and most critical for long-term adaptive capacity. This is an extraordinarily difficult process. It requires identifying which elements of civilizational complexity add genuine value, which are simply overhead that has accumulated through institutional inertia, and which are actively harmful because they drain resources without delivering proportionate benefits. It also requires confronting the political reality that every element of civilizational complexity has constituencies that benefit from it and that will resist its reduction. The people who depend on a particular institution, industry, or practice for their livelihood will oppose changes that threaten it, regardless of whether that institution, industry, or practice is adding value to the overall civilizational system. The political difficulty of deliberate simplification is one of the reasons that most historical simplifications have occurred involuntarily, through the process of collapse rather than voluntarily, through deliberate redesign. The possibility of voluntary simplification, of deliberately redesigning civilizational systems to be less complex, less resource-intensive, and more resilient without waiting for collapse to force the change, is one of the most important and least explored domains of civilizational studies. It requires not just political will, but a framework for evaluating which elements of complexity are worth maintaining and which are not, a framework that takes into account not just immediate economic productivity but long-term resilience, resource sustainability, and ecological integration. Let us now consider what the geological record of mass extinctions tells us about recovery, because the story of recovery after catastrophe is, in some ways, as important as the story of the catastrophe itself. After every mass extinction in Earth's history, life has recovered. Not quickly and not in the same forms, but the fundamental processes of life, the capture of solar energy through photosynthesis, the cycling of nutrients through food webs, the regulation of atmospheric chemistry, have always been reestablished. Sometimes recovery took tens of millions of years. The Permian extinction, the largest in Earth's history, in which more than 90% of all species went extinct, was followed by a recovery period of roughly 10 million years before biodiversity returned to levels comparable to those before the extinction. The end Cretaceous extinction, which eliminated the non-avian dinosaurs, was followed by a recovery period of several million years, during which the mammalian radiation that eventually produced us occurred. These timescales are important to hold in mind because they illustrate what recovery actually means in the context of planetary systems. Recovery after a mass extinction does not mean a return to what existed before. The world after the Permian extinction looked nothing like the world before it. Different taxonomic groups dominated, different ecological structures prevailed, different biogeochemical cycles operated. The system reorganized into a new configuration that was different from the original, but was nonetheless a functioning biosphere. Recovery meant the reestablishment of functional Earth system processes, not the restoration of the specific organisms and ecosystems that existed before. For human civilization, the relevant lesson is not that extinction and collapse eventually lead to recovery. That is true, but not particularly useful. The relevant lesson is that what recovers and what form the recovery takes depends on what survives the disruption. In mass extinctions, the survivors are the organisms that happen to have traits that allow them to tolerate the changed conditions. They do not choose to survive. They do not plan for the post-extinction world. They simply happen to be suited to conditions that became dominant. For human civilization, the analog is the knowledge, the institutions, the practices, and the values that survive a period of civilizational disruption. If a period of severe civilizational stress occurs, what comes after will be shaped by what is maintained through the disruption. The knowledge of sustainable agricultural practices, if it is maintained through a period of disruption, can form the foundation of a more resilient post-disruption civilization. The institutional memory of effective commons governance, if it survives, can provide a template for reorganization. The cultural values of stewardship, ecological awareness, and long-term thinking, if they are embedded deeply enough in the culture to survive periods of stress, can provide the normative foundation for a more sustainable civilization. This is why the preservation of knowledge, both technical and cultural, is not merely a matter of intellectual interest but a matter of civilizational survival. The knowledge that allowed past civilizations to navigate environmental challenges, manage shared resources, and build resilient communities is a resource as valuable as any material input. Losing that knowledge is as damaging to civilizational resilience as losing topsoil or freshwater. Maintaining, transmitting, and building on that knowledge is one of the most important investments a civilization can make in its own long-term survival. There is a paradox at the heart of the relationship between human civilization and the planetary filter, and it is worth naming explicitly because it shapes everything about our situation. The paradox is this: the very qualities that make civilizations capable of great achievement are the same qualities that make them vulnerable to the planetary filter. Ambition drives expansion, but expansion overshoots resource limits. Ingenuity finds new ways to extract resources, but extraction exceeds regeneration. Organization creates complex systems that magnify human capabilities, but complexity creates brittleness. The drive to optimize for current conditions creates efficiency, but efficiency at the cost of resilience. The capacity to delay present costs for future benefits builds infrastructure and institutions, but it also enables the accumulation of environmental debt that future generations must pay. This is not a paradox that can be resolved by simply choosing differently at each decision point. It is a structural paradox inherent in the nature of complex adaptive systems and in the nature of the human psychology that drives civilizational development. The qualities that generate civilizational achievement are not separate from the qualities that generate civilizational vulnerability. They are the same qualities, expressing themselves in different contexts and on different timescales. What this means is that the challenge of civilizational sustainability is not the challenge of becoming less human. It is not the challenge of suppressing ambition, ingenuity, organization, or the drive to optimize. It is the challenge of directing these qualities through institutional frameworks that channel them toward outcomes that are compatible with long-term planetary constraints. It is the challenge of building the feedback mechanisms, governance structures, cultural values, and incentive systems that allow human creativity and ambition to flourish without crossing the thresholds that trigger the planetary filter. This is a more hopeful framing than the one implied by many discussions of environmental sustainability, which often seem to imply that solving the problem requires humans to become less of what they are. The evidence from ecological science, from the history of sustainable resource management, and from the theory of complex adaptive systems suggests something different, that sustainable civilizational systems are not less complex than unsustainable ones. They are differently complex. They are complex in ways that incorporate feedback from the environment, that maintain redundancy and flexibility, that close material loops, that align decision-making timescales with resource recovery timescales, and that distribute the costs and benefits of resource use in ways that maintain effective governance. The question of what we know, and when we knew it, is one that historians of civilizational collapse often find themselves asking. In the post-mortems of failed civilizations, there is frequently evidence that the warning signals were present, that someone somewhere perceived the trajectory and attempted to sound the alarm. The question of why those alarms were not heeded, why the feedback from environmental reality failed to translate into effective civilizational response, is one of the most important questions we can ask. One answer that emerges repeatedly is the problem of cultural lock-in. Civilizations develop not just physical infrastructure but cultural infrastructure, stories, values, practices, and assumptions that are so deeply embedded in the fabric of social life that they become invisible. They cease to be choices and become simply how things are. They shape what is thinkable and what is unthinkable, what solutions are conceivable and what changes are imaginable. Cultural lock-in can be a great strength. The transmission of accumulated knowledge and practice through cultural traditions allows civilizations to build on the achievements of their predecessors without having to rediscover everything from scratch. The farmer who inherits the knowledge of which crops grow best in which conditions, accumulated over many generations of agricultural practice, is better positioned than one who must start from zero. The governance system that incorporates generations of accumulated wisdom about managing shared resources can navigate challenges that would overwhelm a system designed from scratch without that experience. But cultural lock-in can also be a profound liability when conditions change. The Norse in Greenland were culturally locked into pastoral farming practices that were adapted to the European climate from which they came. The cultural assumptions embedded in their way of life, assumptions about the proper relationship between humans and livestock, about the importance of certain foods in the diet, about the social status associated with cattle ownership, were so deeply embedded that adapting to the available Inuit practices was culturally impossible, even when it was physically necessary. The capacity to recognize and challenge cultural lock-in, to identify the assumptions that are so taken for granted that they have become invisible, is one of the most valuable and most rare capacities that any civilization can develop. It requires a kind of reflective self-awareness, an ability to step outside one's own cultural framework and examine it from a position of relative detachment. It is painful because it involves questioning things that are deeply familiar and comfortable. It is politically difficult because cultural assumptions are defended not just with arguments but with power and identity. But it may be essential because the cultural assumptions embedded in a civilization's understanding of itself and its relationship with the world are the most fundamental constraints on what that civilization can imagine doing differently. Let us now turn to a dimension of the planetary filter that we have not yet addressed directly, but that is, in some ways, the most fundamental. It is the dimension of time, and specifically, the question of what we mean when we talk about the future. Human beings are remarkably bad at thinking about the deep future. Our cognitive systems evolved in an environment where the relevant future was days, seasons, and years, not decades and centuries. We have a natural tendency to discount the future, to value present outcomes more heavily than equivalent outcomes in the future, and this tendency is reflected in virtually all of our economic, political, and institutional systems. The standard economic framework of discounting future costs and benefits at a positive rate effectively treats anything that happens more than a few decades from now as negligible. This temporal myopia is the most fundamental source of the civilizational vulnerability we have been discussing throughout this documentary. The consequences of environmental degradation accumulate on timescales of decades to centuries. The actions that cause the degradation produce their most significant costs, not immediately, but over the long run. An economic and governance system that discounts the future will systematically underinvest in environmental protection and systematically overextract from environmental systems, because the costs of overextraction are in the future while the benefits are in the present. Overcoming temporal myopia requires institutional mechanisms that give the future a voice in present decision-making. Various approaches have been developed across different cultures and time periods. The concept of seven-generation thinking, associated with various indigenous governance traditions, holds that decisions should be evaluated in terms of their consequences for the next 7 generations, a time horizon of roughly 200 years. This is not merely a moral principle. It is a practical governance mechanism that extends the effective planning horizon of decision makers far beyond what immediate self-interest would naturally produce. Other approaches to representing the interests of the future in present governance include long-term scenario planning, which explores the long-term consequences of current decisions and makes those consequences visible to decision makers, intergenerational trusts, legal mechanisms that hold assets on behalf of future generations, and constitutional provisions that establish long-term governance principles that are insulated from short-term political pressures. Each of these is an imperfect attempt to solve the same fundamental problem: the difficulty of incorporating the interests of people who do not yet exist into a governance system that is necessarily operated by people who do. The planetary filter does not care about our temporal myopia. It does not wait for our governance systems to catch up to the timescales on which it operates. Soil erodes on the timescale of the next heavy rain, but it recovers on the timescale of centuries. Aquifers refill on the timescale of thousands of years. Climate shifts in response to atmospheric changes over decades, but stabilizes only over centuries to millennia. The filter operates on its own timescale, and our inability to think and govern on that timescale does not change the physical reality. It simply ensures that we are repeatedly surprised by consequences that were entirely predictable from the beginning. As we move toward the conclusion of this documentary, let us consider what a civilization that had genuinely learned the lessons of the planetary filter would look like in its deepest structural principles. Not in terms of specific technologies or policies, but in terms of the fundamental orientation that would guide its relationship with the Earth system. Such a civilization would first and foremost be a civilization that listens. Listening in this context means maintaining the monitoring systems, the scientific institutions, the ecological knowledge, and the cultural practices that translate environmental signals into human understanding. It means maintaining the connection between the condition of the natural world and the awareness of the decision-makers who shape human behavior. A civilization that does not listen to the Earth is flying blind, navigating the complexity of planetary systems without the feedback it needs to stay within the safe operating space. Listening alone is not sufficient. A civilization that learns from the planetary filter would also be one that responds. Response means not just perceiving environmental signals, but acting on them in ways that are timely, proportional, and effective. It means having governance systems that can translate environmental feedback into collective action without the delays, distortions, and capture by short-term interests that have historically prevented effective response. It means having economic systems that account for the full costs of environmental degradation rather than treating nature's services as free goods that can be exploited without consequence. A civilization shaped by an understanding of the planetary filter would be one that maintains humility about its own knowledge and its own judgments. Complex systems surprise us, thresholds are crossed in unexpected places, feedback loops interact in unanticipated ways. The appropriate response to this irreducible uncertainty is not paralysis but precaution. Acting conservatively when the potential consequences of error are severe and irreversible, maintaining larger margins of safety than economic optimization would require, and preserving the flexibility to change course when new information reveals that current approaches are inadequate. Such a civilization would also maintain diversity as a foundational value, diversity of food sources, energy sources, technological approaches, governance systems, cultural practices, and ways of relating to the natural world. Diversity is the source of resilience. It provides the variety of options from which adaptation can be made. It ensures that when one approach fails, others are available. A civilization that has converged on a single technological pathway, a single cultural narrative, or a single governance model has sacrificed the diversity that would allow it to navigate unexpected challenges. Finally, a civilization shaped by understanding of the planetary filter would be one that maintains genuine humility about its own place in the larger story of Earth's systems. We are not the managers of the planet, we are participants in it. We are one among millions of species that have arisen, flourished, and sometimes disappeared in the long history of life on Earth. We are extraordinarily capable participants, capable of levels of perception, understanding, and deliberate action that are unprecedented in the history of life. But we are not separate from the system. We are part of it. Our cities are built on soil that was made by microbes, worms, and fungi over millions of years. Our bodies are sustained by food produced through a web of ecological relationships that predates our species by hundreds of millions of years. Our climate is maintained by the same planetary feedback processes that have kept Earth within the habitable range for nearly 4 billion years. We did not create any of this. We inherited it, and we depend on it absolutely. The Earth has been filtering life for 4.5 billion years. It has seen species rise to dominance and vanish. It has seen ecosystems flourish and collapse. It has seen atmospheric compositions shift from one extreme to another. It has been covered in ice and freed of it. It has hosted environments of extraordinary richness and environments of near sterility. Through all of this, it has continued, guided not by intention, but by the implacable operation of physical law. Human civilization, in the roughly 10,000 years of its existence since the dawn of agriculture, represents a tiny fraction of this story. We are newcomers, we are experiments, and like every experiment, we are subject to the same filter that has operated on every other living system this planet has hosted. The filter does not make exceptions. It does not offer accommodations. It does not grant extensions. But unlike every other experiment that has faced the filter, we know about it, we can see it, we can measure it, we can understand it in enough detail to anticipate its operation and, at least in principle, to choose a different path. No trilobite knew that it was facing extinction. No dinosaur understood that the world was changing in ways that its body was not equipped to handle. No collapsed civilization fully grasped the mechanisms of its own undoing while it was still in a position to change course. We have that capacity. We have the science to understand the planetary systems we are interacting with. We have the history to see the pattern repeating across cultures and centuries. We have the technology to monitor our impact in real time and to project the consequences of our current trajectory into the future. We have the philosophical and ethical traditions to articulate what is at stake and why it matters. We have, in other words, everything we need to understand our situation. What remains is the question of whether understanding is enough. History suggests it is not on its own. Understanding must be translated into structures, economic structures that align individual incentives with long-term collective sustainability, governance structures that give the future a voice in present decisions, technological systems that operate within planetary limits, cultural narratives that make stewardship and long-term thinking not just virtuous but normal, expected, and valued. Building those structures is the great civilizational challenge of our time. It is not a challenge that can be met through any single technology, any single policy, any single institution, or any single cultural shift. It is a challenge that requires all of these simultaneously, operating at multiple scales from the local to the global, across multiple domains from the technical to the cultural, and over timescales from the immediate to the multi-generational. It is, in short, the most complex governance problem that any civilization has ever faced. It is complex because the system being governed is complex, because the consequences of governance choices play out over long timescales, because the actors involved span every culture and every level of social organization on the planet, and because the stakes, the persistence of a civilization capable of the level of human flourishing that has been achieved over millennia, are as high as any stakes could be. The civilizations that came before us are not simply cautionary tales. They are also demonstrations of the extraordinary capacity of human beings to build systems of remarkable sophistication and beauty, to develop knowledge of profound depth and insight, to create art and culture and governance structures of lasting value. The fact that these civilizations ultimately encountered the planetary filter does not erase or diminish their achievements. It contextualizes them. It places them within a larger story that is not one of human failure, but of human striving within the constraints of a physical world. We are the inheritors of that striving. Every agricultural technique, every governance innovation, every philosophical insight, every scientific discovery that our predecessors developed and passed on to us is part of the knowledge base from which we can draw in facing our own encounter with the planetary filter. We have more of this accumulated knowledge than any previous civilization. We have more tools, more understanding, and more awareness of our situation. But the filter does not grade on a curve. It does not give extra credit for having tried very hard. It responds to physical inputs with physical outputs. The only variable that matters in the end is whether the physical relationship between our civilization and the Earth systems is aligned or misaligned. Whether we are operating within the regenerative and absorptive capacity of the planet, or whether we are in overshoot. Whether our civilizational metabolism is in balance with the planet's metabolism, or whether it is depleting the capital that sustains it. These are empirical questions, not philosophical ones. They have answers that can, in principle, be measured. And the measurement of our current relationship with the planetary systems we depend on is the most important scientific and governance challenge of our time. There is one final concept that we need to address before we bring this documentary to a close, and it is the concept of agency. Throughout everything we have discussed, there has been an implicit tension between determinism and choice. On one hand, the planetary filter operates through physical laws that are not negotiable. On the other hand, the historical record shows that civilizations have made choices that significantly affected their trajectories, that some managed their resources sustainably for extended periods while others depleted theirs rapidly, that some adapted to environmental change while others remained rigid and perished. This tension is real, and it reflects something important about the nature of complex adaptive systems. Such systems are neither fully determined nor fully free. They operate within constraints that are real and binding, but within those constraints they have genuine degrees of freedom. The constraint of gravity cannot be escaped, but within that constraint, an enormous range of structures and behaviors is possible. The constraint of the second law of thermodynamics cannot be violated, but within that constraint, the most elaborate and beautiful forms of order and complexity can arise and persist. The constraints of the planetary system cannot be overridden, but within those constraints, civilizations can choose to operate sustainably or unsustainably, to maintain feedback or to ignore it, to build resilience or to sacrifice it for short-term efficiency. Agency, in the context of the planetary filter, is not the freedom to escape the constraints of the physical world. It is the capacity to perceive those constraints clearly, to understand their implications, and to make choices that operate within them rather than against them. It is the capacity to build institutions, technologies, and cultures that align human behavior with the physical reality of a finite planet. It is, in the end, the capacity to choose not to be filtered out. This is not a small capacity. It is an extraordinary one, unique in the history of life on this planet. And it places on our civilization a responsibility that no previous civilization has borne, the responsibility of awareness. We cannot claim ignorance of the filter. We cannot claim that we did not see the signals. The signals are visible, measurable, and documented in extraordinary detail. What we can claim, if we have the courage and the wisdom to act on our knowledge, is that we were the first civilization to understand the filter and to choose a different path. Whether we will make that claim, history will record. The earth will register it, not with judgment or approval, but with the simple, implacable accuracy of a physical system. It will register whether the carbon dioxide in its atmosphere continues to accumulate or begins to stabilize. It will register whether its soils continue to erode or begin to rebuild. It will register whether its freshwater systems continue to be depleted or begin to recover. It will register whether its biodiversity continues to decline or begins to recover. It will register in every molecule of every ecosystem and every shift in every atmospheric current the cumulative consequence of every choice that our civilization makes. The filter is always operating. It never rests, it never relents, it never forgives. But it also never stops offering the possibility of alignment, the possibility that a civilization will find its way to a relationship with the planetary system that allows both to continue, the civilization in its complexity and creativity, and the planet in its extraordinary, ancient, self-regulating grace. We began this documentary with a question: what if Earth selects which civilizations continue? We have now traced the full arc of an answer. The selection mechanism is not mystical. It is not intentional, it is not designed. It is simply the operation of physical systems that have been functioning since long before life existed, and that will continue functioning long after we are gone. The selection occurs through the simple, relentless feedback between what civilizations do and what the physical world does in response. What civilizations do: they extract, they produce, they grow, they build, they consume, they discard. What the planet does in response: it erodes, it warms, it floods, it dries, it shifts, it crosses thresholds, it reorganizes. The civilizations that align their extraction, production, growth, construction, consumption, and disposal with the planet's capacity to regenerate and absorb are in effect aligned with the planet. They are operating within the selection criteria. They persist. The civilizations that exceed those capacities, that take more than the planet can regenerate, that emit more than the planet can absorb, that disrupt more than the planet can rebalance, are in misalignment. They are operating outside the selection criteria. And the filter, patient but implacable, eventually corrects the misalignment, not through punishment, not through judgment, but through physics. We are the civilization that knows this. We are the experiment that has become self-aware. We are the first in the long history of life on this planet to look at the filter clearly and to understand what it demands. What we do with that understanding will not change the filter. The filter is not changed by understanding it, but it might change us. And if it changes us, if we allow it to shape our institutions, our values, our technologies, our governance systems, and our sense of our place in the long story of this planet, then we will not be the civilization that the filter selected against. We will be something new, something that the 4.5 billion year history of this planet has never before produced, a civilization that chose alignment, a civilization that earned its continuity. A civilization that proved that awareness can become wisdom, and wisdom can become action, and action can become a different kind of story than the one that has ended so many times before. The planet is waiting, it is patient, it has all the time in the universe. The question is whether we do. Thank you for joining us for this exploration of one of the most profound questions in the history of human civilization. The relationship between our species and the planet we inhabit is not simply a backdrop to our story. It is the story. It has always been the story, and it will continue to be the story long after the particular chapters we are living through have been written. If this documentary has given you a new way of seeing that story, a new framework for understanding the deep dynamics that have shaped civilizational rise and fall, and a new appreciation of both the challenge and the possibility that confronts us now, then it has accomplished its purpose. Please share your thoughts in the comments. Let us know where you are watching and what struck you most deeply. be sure to subscribe to the channel for future explorations. And carry with you as you move through your own corner of this ancient and extraordinary planet the awareness that the ground beneath your feet is listening. It always has been, and it always will be.